Everyone, good morning and welcome to the morning session of the last day of the winter school. Today we have Benny Pincus, who's going to talk about private set intersection. Benny is the director of the Cyber Research Center at Bar-Ilan University, Israel. He received his PhD from Weizmann Institute in 2000, and he has worked in the research lab of Intertrust Technologies, HP, Google, and VMware. His main research areas are cryptography, computer science, and privacy, with a focus on secure computation. We're very happy to have Benny here. Benny, the stage is yours.
Thank you, Kamit, and I'm very happy to be talking at the school. I'll be talking about private set intersection. I'm going to have 2 hours. In this first hour, I'm going to show a quick introduction to PSI, private set intersection. Then I'm going to talk about the basic PSI protocol, which is based on Diffie-Hellman, but also about its relation to Oblivious Pseudo-Random function evaluation, or PRF. And I'm also going to talk slightly about the technology behind the CSAM detection system that Apple rolled out this summer and then discontinued. Okay, so let's go to the talk. So I'll be talking about introduction to PSI, Diffie-Hellman-based PSI, and PSI from OPRF, and the Apple CSAM detection system. So what is PSI? So we can think about the following functionality. We have 2 parties, Alice and Bob. Each one of them have a set of inputs. Alice has x1 to xn. Bob has y1 to yn, and Bob should learn the intersection of the 2 sets and nothing else. And we can also think about a protocol where Alice also learns the output. And we can also think about computing functions of the intersection, some simple functions like the size of the intersection, or whether the intersection is greater than some threshold, or more complex functions. And we can also think about a multi-party version where there are more than 2 parties, and we want to compute the intersection of all of the sets. So PSI has surprisingly many applications. So it can be used for information sharing between different parties, say that have threat information, strange things that happened on their network, and they want to compare them. They can be used. It can be used for checking matching between different parties. If you look at databases and join operation, then they're basically PSI, computing the intersection. Also, when you do analytics, many times what you want to compute is the condition probability of some feature A given some feature B. And when you compute the conditional probability, you need to compute the probability of the intersection of the 2 things happening. There are also applications for identifying mutual contacts between users and all the context of a new user of the Signal app and all current users of Signal, or for computing ad conversion rates, and I'll describe this example in more detail. So for analytics, you can think about an example, say, where a university knows the IDs of workers and students, and the government know which persons were vaccinated, and you want to compute the percentage of people that were vaccinated inside the university, okay? So you don't want to reveal this information to each other, just to compute this percentage. So for this, you need to know how many people are in the intersection. Another interesting example is this story from the New York Times, where apparently there are people who go to many fertility clinics and serve as sperm donors in many of them because they want to have many children. And then the fertility clinics want to identify, if the certain person came to more than one clinic, but otherwise they want to keep the identities of sperm donors private. And this is another example from very interesting Israeli startup, where the cases where you have a merchant, say Alice, that has a new customer, and you have a network of merchants and banks, and each one of them has lists of a few million customers. And when the merchant comes, she wants to know what the other merchants in the network know about the customer. Is it a good guy, a bad guy, what they know about it? And she wants to do this while hiding the identity of this customer, and they want to hide the identity of their customers. But together, they want to learn something about new customers. So in general, Alice, the merchant, has a new customer. Each other member has a set of customers and some rating. And Alice wants to learn the rating of the new customer according to the other members. Okay, and they should not learn who's the new customer. And you can do other things like, say, if Alice receives a purchase from a certain credit card to a certain address, she wants to know if the other merchants had also purchases by the same credit card to this address, say, a few days ago, and there was no dispute, so maybe that's okay. And what's interesting to note here is that here Alice's set contains only a single item. So here we compare one item to many items. So in addition to computing the intersection itself, we might want to do analytics on it. So here we have the sets, but Bob doesn't want to learn the intersection, but he needs to learn some function of the intersection. Okay, say the size of the intersection. And another option is with payloads. So here, each item has a payload associated with it, say the rating, and you want to compute some function of the items in intersection and the payloads. So here it's a more complicated, more complex function. And as an example, there's a, these days very known application of Google that use PSI for ad conversion rate. Ad conversion measurements. And so what happens is that, say, a credit card knows who came to a certain merchant and made purchases. And Google they know which users saw a certain ad, say, for that merchant. So basically, what you want to learn is how many purchases were made by people who saw this ad. So here you don't want to compute the intersection, you want to compute the sum of the transactions made by people that, say, saw the ad yesterday and came to purchase something today. And this purchase can be in an offline place, say in an ice cream stand. Okay? And of course, what they do is probably more complicated, but this is the basic thing that they want to do here. So some computation on data associated with the items in the intersection. Okay. So why did I investigate PSI? So it's relevant for many applications, but this, it took us time to identify this. But also, this is a function that cannot be efficiently solved by generic MPC. So generic MPC works by computing over a circuit, which computes the function. And if you want to build a circuit that computes the intersection, basically you have to compare n items of Alice to n items of Bob. So the simplest way to do that we'll have to do n-squared comparisons, and that's too many. I mean, if say n is a million, so the circuit will be too large. So here is a case where you need to design a specific solution for a problem for which the generic MPC is not efficient enough. And also a nice property is that the solutions turned out to be quite interesting. So that was a nice extra when we worked on this. So one approach to design PSI protocols is using oblivious pseudo-random functions. So a pseudo-random function, you can think of something like AES. And here, if I don't know the key and I just get to see the output, it looks random to me. It's pseudo-random. So a PRF is keyed with a function k, and someone who does not know the key, the output seems for that person to be pseudo-random. Even if that person knows the input or even chooses them, the output is still indistinguishable from random. So this is a pseudo-random function. And a protocol for oblivious pseudo-random function evaluation, or OPRF, is a protocol for securely computing a PRF. So Alice provides an input X, Bob provides a key K, and then Alice learns FK of X, say the encryption of X with AES, with the key K, or another pseudo-random function. Another version, which seems strange at first, is that Alice provides a key K, an input X, and then the functionality chooses a key K, gives it to Bob, and gives to Alice FK of X. So Bob does not choose K here, just he's given K by the functionality. After he's given K, he can compute F on any function that he wants, okay? but it doesn't choose K. So this seems odd, but apparently it's important where it's useful where it's not important for Bob to choose the key. It's only important for him to have a key which Alice doesn't know. And in PSI, this is the case. So in PSI, we're mostly going to use this version because it's more efficient. Okay, so here's an example of a specific pseudo-random function based on DDH. So this is the DDH assumption. I hope that most of you know it. So in a DDH group, giving a generator G and random A, B, and C, you cannot distinguish between these two tuples. So this is a tuple G to the A, G to the power of B, and G to the power of AB. And this is just, random 3 elements in the group. And here the values should be in the right range, etc. So this is, very basic assumption in cryptography. And here's the PRF based on it. So let's G be a group in which the DDH assumption holds. Let H be a publicly known random function mapping into G, and we model it as a random oracle. And key is the K. K is the key. And the function is very simple. Given an input X, we hash it using H into the group, and we raise to the power of the secret exponent key, K, the secret key K. And the claim is this is a pseudo-random function. Okay. Now, typically, we implement this in elliptic curve groups, using elliptic curve cryptography. But for me, it's easier to describe this in this notation, okay, like computing modulo P. But most implementations are in elliptic curve groups. So here's a protocol for securely computing this pseudo-random function. So Alice will learn f of x with Bob's key without learning the key. So Alice chooses a random value r, and she sends to Bob h of x to the power of r. Bob raises this to the power of his secret key k, sends the result to Alice, and Alice takes the root of what she received, and she computes h of x to the power of k. Okay, so she received the output of the pseudo-random function. So why does this look to be secure? So the only thing that Bob sees is a value in the group raised to a random exponent. So this is uniformly distributed, so Bob doesn't learn anything. And what Alice sees is basically 2 values. This is random. This is that value raised to the power of k. But actually, given her input and output, her input is x, and her output is the output of pseudo-random function, h of x to the power of k. So she can compute these 2 values that she sees. So she compute them by taking x, computing h of x to the power of r that she knows, and taking the output of the function, raising it also to the power of r. So Alice, giving her input and output from the protocol, which she should learn, can simulate her entire view. So this also seems to show that she is secure, and you can easily prove security based on that. So actually, this OPRF is now quite widely used. There's even an internet draft defining it. And you can also think of variations where this is a verifiable OPRF. Basically, the server can prove that in all invocation, it uses the same key. So basically, the server publishes G to the K, and whenever it runs the protocol, it proves to Alice that whatever she sent to him, he raised to the same power K. And this is today quite widely used. So how can we use it for PSI? So I'll describe here a very known PSI protocol, the most basic one, designed by Catherine Meadows in 86, I think, and then redesigned afterwards over and over by other people. And I'll describe it as using an OPRF. So Alice has, of course, the initial descriptions were not describing it as an OPRF, but this is how we're going to describe it. So Alice has this set of values, and Bob has this set of values. She chooses the random alpha, and Bob would choose a random key beta for the OPRF. Alice sends to Bob age of each of her values raised to the power of alpha. And usually we use elliptic curve groups to do this. Bob takes each of his inputs, computes age, and raises to the power of beta. So basically, he sends the output of the PRF on his inputs. And then he takes all of the values received from Alice, raises to the power of his key beta, and sends to Alice. Now, Alice takes these values, takes the alpha root, okay? So basically, she gets her input, applying age to them, and then just raised to the power of beta. And then she compares the values she received from Bob to the values that she computed. And if one of the xi's is equal to one of the y's, then she see equality. So this is the entire protocol. First, what's nice about it is very simple. Okay, if you think about it for a few more minutes, you completely understand it, and it's also very simple to implement. This is extremely important. Now, and we describe it as an OPRF. Okay. Now, why is it secure? So before describing this protocol, I should have asked you to design a PSI protocol, and most people come with the following insecure version of PSI. So the insecure version is for Alice to take her inputs, send to Bob some hash function of the inputs, SHA of her inputs, and Bob will compute, SHA of his inputs and compare them. So this initially seems secure for non-cryptographers because this function is one way. So given the output, you cannot reverse the function. But if Alice's inputs come from a small domain, say it's a phone number, then Bob can run a dictionary attack over all possible phone numbers, compute SHA over all these numbers, and compare them to the values he received from Alice. So the problem, the attack against this, trivial but insecure PSI protocol is that Bob can compute the function himself over the entire domain of possible inputs for Alice. What's nice in the OPRF protocol I showed you earlier is that what Bob sees here is a function of Alice's input, but this function depends on the alphas that only Alice has. And what Alice sees is a function of Bob inputs, but this depends on beta that only Bob has. So they cannot do this dictionary attack. Okay. So this is basically what I said. So you can also prove this by simulation. Bob can simulate his view in the protocol because basically what he sees here is pseudo-random. This is exactly the output of the pseudo-random function with a key that only Alice has. And basically what Alice sees here, these are pseudo-random values, and these are values which either are equal to, for items which are not in the intersection, the pseudo-random, and for items which are in the intersection, they're basically one of the values that Bob sent raised to the key that Alice has. So Alice can simulate this. This takes some more time to prove, but she can simulate her view. Any questions so far?
Yes, so there is one question.
Okay.
So the question is, can PSI be considered as a special case of PIR when only one party gets the output?
Okay, that's a good question. They both talk about two servers and learning something, while hiding what you want to learn. It's also several differences. So first in PIR, there's only one item, not many items. And mostly in PSI, the main difficulty is that you compare many items to many items because you don't want to do the n-square comparisons. Another issue is that in PIR, at least in the basic definition, you care about hiding the query from the server, but you don't care about the client learning more than one output. More than one. So in PIR, you care about preserving the client privacy. So the server should not learn what the client is querying about, but you don't care about the server privacy. You care about, so in theory, the client can learn about more than a single item, more than about the intersection. Also in PIR, the focus is about the communication being sublinear, and in PSI, it can be linear communication. But sometimes we combine PIR in PSI solutions. Okay, so let me continue. So what we showed you is basically this protocol is a template for running PSI, okay, using OPRF. So basically what you do, you run an OPRF version where Alice gets the output of the OPRF on all of her inputs. And Bob sends to Alice the output of the PRF on Bob's inputs, and then she can compare them. So this is basically what we did with a specific PRF, but we can do it with other pseudo-random functions. Now, thinking about it, Bob doesn't have to send to Alice the PRF output of his inputs, because she's just going to compare them to what she computed. So instead, he can send to her shorter outputs, just long enough so that she can compare them to what she computed and have a very small false positive probability. Okay, so you can have hash this output to be much smaller according to what false positive probability you're willing to tolerate. And apparently, you don't have to send the list of outputs. What Bob should send is a data structure called the dictionary, which enables Alice to take what she learned in the OPRF protocol and check if it's in this list. And by sending a dictionary, you can even compress the message from Bob even further. So where is this important? It's important when you do PSI of sets of unequal size. So Bob sends to Alice a dictionary encoding of the PRF outputs on his inputs. And then for each input of Alice, they will run an OPRF in which she'll learn this output and check if it's in the dictionary. Now, if Bob's input is much larger than Alice's, then he can compress all these values to be as short as possible based on whatever false probability that we allow. And then for each item of Alice, they'll just do a computation which has like a constant overhead. And also, Bob can send these values to Alice even before she learns her input, and then she can check for a match whenever she has an input. So gradually, whenever she has an item, she can compare it to Bob's values. So this is very useful where her input size is much smaller than Bob's. Now, there are many implementations of OPRF, and basically what we want to use is the one that gives us the best performance for PSI. And I won't describe them. I only describe the basic one based on Diffie-Hellman and random walk. And for some applications, we need verifiable OPRF or security against malicious, and sometimes we use OPRF for other applications, but we're talking about PSI. So this was the first half of my talk. Any questions?
No questions.
Okay. So in the other half of this hour, I will be talking about a very recent PSI protocol that received a lot of attention. And this was a system deployed by Apple, or announced by Apple for detecting CSAM, which is child pornography, or it's called child sexual abuse material. So this is my interpretation of it, both based on how I read the documents that Apple published. Okay. And what's important about this case is that it received a lot of publicity and a lot of debate about, social, legal issues of this solution. People talked less about the technical issues, and I want to focus here only about the technical issues. We can devote an entire hour just to discussing the high-level social issues, but I'm not going to discuss them here. And what's nice about these issues is that, this quote from Mariana Pfefferkorn from Stanford, where she says, about this system, that may your research area be relevant to current affairs is may you live in interesting times, curse disguised as a blessing for the academic set. So this is, a saying which is, known in many languages as it's a blessing, but living in interesting times might also be a curse. And when your research is relevant to, the world, it seems like a blessing, but it's also a curse because it makes things much more complicated than working in complete theory. And in this case, it was, a huge, headache. So just some background. So CSAM is child sexual abuse material, which is terrible material, and it's against a law and against any norm to be using or viewing these images. But apparently the internet is overrun with such images. And this is from the New York Times. Last year, tech companies identified more than 45 million online photos, okay? Which is harrowing, I mean. Okay. Now, the question is what you do about it. So all companies, including Apple, when they received a court order, okay, they provide what the court asked from them, or some requirement for law enforcement, okay? But this is when they have a requirement, at least in the United States or Western countries, if you have a court order or requirement, a lawful requirement for law agencies to get to a specific item, okay? So they tell you, give us the data of this person. And this depends on the law in different countries, okay? This is not about scanning all your data or all the data of all users all the time and looking for these horrible pictures, okay? Still, you want to be searching for this data, okay? So what happened in previous years, it was reported that Facebook 20 million such photos on these. And the companies, when they find and Apple only found 250 such photos last year, okay? So, of course, it's, case that, Apple, it's the case that Apple was not searching for these photos because they didn't want to search photos unless they get a court order, okay? Also, what we're going to discuss here is not about searching for photos in phones or in messaging apps. It's only about photos which are uploaded to cloud storage, okay? So what do other cloud companies do, okay? There's an organization in the United States called NCMEC, or National Center for Missing and Endangered Children. It's the only organization outside of law enforcement which can view these photos. It computes a hash of these photos, some hash which is supposed to be resilient to small changes like cropping and changing the size, etc. So it computes this hash using a known hash algorithm, which they try to keep private, but it's not secret. They send the hash list to cloud companies like Facebook or Google. And then when you store your photos on Facebook or Google, they go to each photo, they compute the hash of that photo and compare it to this hash list. And when they see a match, they report it to law enforcement because they must report it, okay? So this is possible because your photos are stored in the clear, okay? And they can scan them, and they're not required by law to do it, but they do that. And Apple didn't want to scan your photos, okay? Now, just to make it clear, they are only looking here for matches with known content of photos that, as far as I know, were declared by a court to be CSAM, okay? I think they even know the names of the children in each of these photos, okay? They're not analyzing your photo and see if you have a nude, photo of your children, etc. They're looking for specific known photos, okay? So anyone holding these photos is definitely operating against the law, and the companies are reporting them. And Apple did not do that, okay? So the system that Apple wanted to design, okay, was required to have the following properties. Apple always say Alice instead of Apple, but it's Apple, of course. Apple doesn't learn anything about images that do not match the known CSAM list. So they don't want to look at your other images, other photos. Apple doesn't want to access the photos of a specific person until they identify, say, at least 30. That's an arbitrary threshold that can be changed. matches from that specific user. So if you have like 1, 2, 29 photos by accident, that's okay. There's a certain threshold. If you have more than that, only then they'll be able to open your photos and check them. They want the risk of incriminating, innocent people to be extremely low. And also, once they identify that someone has at least 30 such images, then the photos will be opened, or some low resolution version of them, and someone will manually look at them, and only if they see something suspicious, they will report this. So this is to protect users against Apple watching the photos or reporting an innocent user. They also want to have the following requirements. Users cannot access or view the database of, see some images or even the hashes, because then they'll be able to check if a certain image is in this database. And users cannot identify which images of them were flagged by the system as CSAM. So basically, the only output that the user sees from the system is if that user had more than 30 images, then maybe the police will knock on that user's door. Any other output the user doesn't see. Okay, this is to protect, I would say, society from users who try to use the system to identify, what images are in this CSAM data. So this is an ideal view of how we'd like to, use MPC to implement this. So NCMEC provides a hash list to Apple. Apple provides it to a trusted, an ideal word to a trusted party. The device provides hashes of uploaded photos. If the number of matches is smaller than 30, nothing is done. If it's more than 30, then Apple gets the identities of the matches. So this is what we want the trusted party to do. And it seems like a PSI protocol. You compute, say, the intersection. And the device will compute the hashes, compute the intersection. I mean, there are some requirements which are dependent on the application, okay? And any solution might solve them. And the ideal functionality, it's a bit, hard to define in it these requirements. So first is that, okay, we want Apple to provide the same hash list to all users, so they cannot check in my iPhone for certain set of photos and say in other people look for other set of photos, say in other countries. And this is to protect, say, governments from asking Apple to look for, say, political photos or something like that. And also, this should be the photo received from NCMEC. Okay, the list received from NCMEC. So you can do this using actually zero-knowledge proofs. You can prove this. It's not very hard to do it, but I won't discuss it here. Also, what happens is that the user doesn't, we don't compare all the photos of a user at the end of the year. We want to compare them one by one as the user uploads them. And this should be a non-interactive protocol. So he uploads the photo and then he doesn't interact more with the server. And also, once you get this list, they want humans to look at the photos before reporting people, just to be on the safe side. So basically, this entire system is just to, filter suspicious users from, all, billions of users. And then the suspicious users will be inspected by humans. Okay, so how does the system work? NCMEC sends Alice Apple the hash list. Apple encodes the hash list as Diffie-Hellman tuples, and I'll describe it in details, in a Cuckoo table, and sends this encoded hash table to the device as part of the operating system. The device, when you upload a photo, you compute a hash of it. You compute a key based on that photo and this hash table. You use that key to encrypt a low-resolution version of the photo, and you send it to Apple. And then the PSI magic, if there are at least 30 matches, then Apple will be able to decrypt the low-resolution versions, inspect them manually, and report. So this is how the system operates. And some things to notice. First, Apple only gets the hash list. They don't see the photos. Actually, it's against the law for them to see the photos. Okay, and look, in different countries, they might be different agencies. Okay, so what's considered CSAM in one country might not be CSAM in another country. So that's a big issue for them. Then they encode the hash list. So what the user receives, the device receives, doesn't receive the hash list, but some encrypted version of it. Okay? So the device doesn't see the hashes. Now the update is received as part of the operating system. This ensures that all users all the world receive the same hash list. Okay, so they cannot target me specifically because I receive the same operating system update as others, and also updates, happen every few months. The list cannot change too often. Now, this hash is only computed for uploaded photos as part of the upload mechanism. So it's not about photos on my machine, only about uploaded photos. However, most users upload all of the photos to iCloud, but they can choose not to. And then you compute a key. With the key, you encrypt. And if there are more than 30, at least 30, but not less, then you can Apple decrypts and inspects manually. So this is like some things that they had to focus in the design. And I think that here, it's a good time to ask if there are any questions so far.
No questions so far.
Okay. So what we see here is that the device doesn't learn the hash list. The device doesn't learn if there's a match because it doesn't get any output in this protocol. And Apple do not learn anything about non-matched photos because only if there are more than 30 matches, they can decrypt. So how do you do this? So here we get to the PSI part, which is also based on Diffie-Hellman. Also, everything is in elliptic curve groups, but I use exponentiations. So the server, when it prepares this hash table that will be sent to all users, it picks a random secret key, exponent A, which will be global for the entire world, okay? And then they construct a cuckoo hash table, but you don't have to know what cuckoo hash is, hash table, storing the hash list. So for every photo hash X that they received from NECMEC, they store the value, okay, say X is mapped to the group, and they store the value X to the A in the table in location T age of X. So this is a function which maps to a location in the group, location in the table, okay? This is not the hash function that was used by NECMEC to hash the image to a value. And then what you use, the hash of the function, you raise it to the power of A and you store it here. Okay, so actually this is a cuckoo table where each item can be stored in 2 locations. Okay, but just to simplify things, say that it's stored in just 1 location. And also, if there are collisions and some items we cannot store, we just drop them. And in some locations, the table remain empty. You just put them random entries. Now, basically, what you compute here is X to the A in a Diffie-Hellman group where A is secret. And since X is already the output of a hash function, this is the pseudo-random function we discussed. So basically, what Apple stores is a pseudo-random values. What Apple puts in empty entries is random values. So the whole table looks completely pseudo-random to users. They don't learn anything. So what the users, the client, get as part of the operating system is this table and G to the A. So this all looks completely pseudo-random to them. Something else to note is that if you send a table which is not large enough and you have too many collisions, then you cannot put all items here. Okay, so in terms of collisions, they say just drop some of the items until you can fit all items in the table. Okay. Now, usually when we talk about PSI, we don't want to do this. We have the inputs. We want to compute the intersection of the input sets of Alice and Bob. We don't want to drop any item, and we work a lot to make sure that we don't drop any item. Here, basically, they want to compare photos to a list of maybe 200,000 and see some images. If, say, 10% of these images they have to drop from the table, okay, and this is a random subset. So basically, for the bad users, 10% of the bad images will not be identified. But if someone is bad, then there's also very good probability that these photos will match the 90% of the CSAM database, which they don't drop. So here they don't care about dropping some of the photos. Okay. So what's important for security is what's called Diffie-Hellman self-reduction of now and Reingold. Okay, so look, this is a Diffie-Hellman tuple. G to the A, G to the B, and G to the AB. Suppose we take random values C and D, and we compute G to the D, this is D, and times T to the C. And we also take this value, G to the L, L to the D times P to the C. So basically, we take a random Diffie-Hellman tuple, take the first and third items, raise them to the power of D and C. This is the first value. Takes the second and fourth item, raise them to the same powers. This is the second value. Now, what you see, the red items are the blue ones raised to the power of A. So basically, if this is a Diffie-Hellman tuple, then S is Q to the power of A. Okay? S is Q to the power of A. If this is not a Diffie-Hellman tuple, then you can show that these two values are uniformly random. So S is completely independent of Q. Okay? There's no relation between them. Okay, so the important thing here is that if we start from Diffie-Hellman tuple, we get that S is Q to the power of A, and whoever knows A, Apple, can compute S given Q. Otherwise, S is completely random. This is what they're going to use. Okay, so what happens on the client side? This is the most important thing. The client has a photo. Okay, so it computes the hash of the photo, this photo DNA hash. It has the ID of the photo. And it also has some associated data, which is a low resolution version of the photo. Okay, it picks random C and D, and it computes Q, which is hash of photo X to the power of C, G to the power of D. In S is what you have in the table that you received from Apple for the location of that photo, raised to the power of C. And G to the A that you also received from Apple raised to the power of D. Now, if this photo happened to be in the database sent by Apple, then what you have in the table here would be X to the power of A. This is how we constructed the table. In that case, it would be X to the power of AC, G to the power of AD. Basically, we started from a Diffie-Hellman tuple, and what we get is that S is Q to the power of A, because here you get XAC, GAD, so S is Q to the power of A. Otherwise, if S, what you have in the table in this location, is not X to the power of A, then this is completely random, using based on the random self-reduction of Diffie-Hellman. So the idea is the client computes these two values, okay? He's going to send Q to the server as part of the upload, and then use this S as a key. Now, if the item that client uploads is a Diffie-Hellman tuple, then then S is Q to the power of A. The server knows A, and the server can compute this key. Otherwise, the key is completely random. So basically, the nice thing here is that the client computes a key that for items which do not match the system database is completely random. And for items which do match the system database, the server can compute that key easily. Okay, so just stopping here. The client sees a table, but this is completely pseudo-random. If the client doesn't know the key A that only Apple knows. And for items which are not in the table, the client encrypts, I didn't say what it encrypts, but the client encrypts something with a key which is completely random. Okay. Any questions?
Yes, there are several questions.
Okay.
So going back to the protocol description as in before the technicalities. So there's one question on, yes, here. Do you know how big the encoded hash table is? Because it could be rather large because there could be a lot of reported images.
Yeah, okay, so we just said what's in the encoded hash table. For each item, we store one or two values in an elliptic curve group. So say we store 32 or 64. No, we store 250 bits or 500 bits per item. Okay, so if you have say 100,000, 200,000 items here, it's going to be megabytes, but it's part of the operating system. It's the operating system update. It's fine.
Okay, so one more. Why does the cuckoo filter need to be part of the OS? Okay,
so this is not something for the PSI protocol. It's something for the general picture. So and a possible attack would be that the government wants Apple to track me, and they tell them, give Benny a specific, hash table that looks for political images or for, something which is specific for me. Okay, so by putting it as part of the operating system, and the operating system is universal, all people all over the world get the same operating system. You can ensure that everyone gets the same, list of hashes. Okay, so you cannot do different things in different, to different people or different countries. Also, the operating system is updated not very often, every few months. So, and this, for database also is not uploaded very often. So this is to ensure that, governments cannot track people, specific people or change what they track for very quickly.
All right, another question. For the cuckoo table, can you specify the hash function in such a way that all the hashes can find a place in the table? Because you want to compare image hashes against all the hashes in the CSAM list.
Okay, so this is the cuckoo table. And okay, those who are familiar with that know that the size of the cuckoo table should be like 2 plus epsilon times the input size. And when you look at the documentation that the Apple put, it's like 1 plus epsilon times the input size. Now, this seems like a typo, okay, or maybe epsilon is 1 point something, but it's not a typo. So actually, they had a cuckoo table which is quite small, okay? And this is to improve on performance because this basically cuts the size of this thing by a factor of 2, okay? So by having a smaller cuckoo table, okay, you inevitably you're going to have a lot of misses. So something like, I just invented a number, 10% of the items, but you can run a simulation, okay? You will not find a place for them. But for this specific application, it's not bad because you just, instead of looking for a huge database of CSAM photos, you're looking for something which is, 90% of that database. And it's not, a random subset of that size. So any bad guy is likely to have, many items for that 90% section, subset of the bad database. So the size is about 1 plus epsilon times n. I'm not sure what epsilon is.
Okay, right. So another question, is the client honest? Otherwise, they can just always use a random key.
Okay, so the client is running the Apple operating system, and you assume that it follows the protocol. Because otherwise, yeah. Okay. So I want to continue, and then we'll ask at the end because I want to make sure that I can. Okay. So, the important thing here is you want to do threshold PSI. If there are less than 30 matches, Apple should not learn anything. Okay. So it goes like this: the client picks a random master key. This is associated data key, AD key, for all items. For each item, it takes the data of that item, which is the low resolution version of the image, encrypts it with this master key. Then it generates a Shamir share of this master key with a threshold of 30. It encrypts these two values, where S is the key that Apple can only learn if the item is in the CSAM database. And with this key, it does an authenticated encryption of the pair of the encryption of the photo and the share. So if there's no match, Alice learns nothing. Otherwise, Apple Apple learns a share and encryption with the key. Okay, so it learns a share and encryption of the key with the key. After 30 such shares, it can recover the key and learn everything. Otherwise, it cannot recover this. So this is good, but the problem here is that if this is authenticated encryption, Apple learns whenever it sees a share. So then they can see, and the government can ask them, tell me for which persons you got 29 shares. So we cannot decrypt anything, but we know that these are not, saints because we had 29 matches for them. Okay, and Apple want to hide this. So they want, if they'll have less than 30, they don't want to learn anything. So they want to somehow hide who has 29 matches, who has 28 matches, etc. Okay, so you want to hide the number of matches. So what happens is that the devices, the phones, will also send at random dummy matches. So messages that the servers will be able to decrypt, and they'll get something that looks like a share and like an encryption, but this is a dummy share. So what the server will end up with is some real shares and some dummy shares, and it must be able to decrypt whenever the number of real shares is more than 30, at least 30. So basically what we get here is a kind of an error correction problem. Okay? And the problem is that the server doesn't know before it gets 30 real shares, which are the real shares, which are the dummy shares. And the solution is based on a decoding algorithm of Corpus Smith in Sudan. And basically what you have is like enhanced Shamir shares. And if you want to be able to decrypt, identify given state T, which is 30 correct shares, and S dummy shares, you use the system. The caveat is that the size of each share is now increased to be, by a factor of S plus 1. So each share is not one item in the field, it's like S plus 1 times an item in the field, which is much larger. So if, say, T is 30 and the number of dummy elements is at most 100, some random distribution, then each share will contain 101 field elements, which is, for me, it looked, very bad. But actually, they said it's not that bad because, each share is much larger. But in the context here, you upload a share together with a photo. So the photo is like, 2 megabytes. And then here you're going to upload, 100, items in a elliptic curve group. That's nothing compared to the image. So this is important for PSI. Like you should think of the context. Here we don't care about increasing the communication of PSI because the other parts of the system is much less efficient. So the associated data, what we encrypt is a low resolution visual derivative of the image. If you have 30 matches, then you can decrypt this because you get the share, and then human operators can check these low resolution versions. If they look like CSAM, they report the user. Okay. Now, there are many potential problems which I didn't discuss here. And these were like the big problems, okay? First, they might be false positives. So they set the parameters so that happens with very low probability. They can be attacks like on the machine learning, trying to attack the photo DNA algorithm. I think that there are good solutions for that, but in this context, but I won't go into them. Another issue is that people didn't like the fact that Apple is scanning things on our devices. And this is, I can understand this. But, there's a problem. I don't want to go into this, but there are 3 things which are all good. One is we don't want people to be using CSAM because it's obviously bad. The second thing is that we want our storage to be end-to-end encrypted. So we don't want servers like Apple or Google or Facebook be able to see our photos. This is also something that we want. And another thing is that we don't want them to run any scanning on our devices. Okay, you cannot have all these three things together. If you want to scan for CSAM, you have to either do it in the cloud or some component together with the device. So here is an attempt to find, some trade-off between the different requirements. The public didn't like this trade-off. Okay. Okay. Another issue is, who controls which items are searched for, governments, etc. So Apple tried to somehow control this by having like a single list for the entire world, and they said that they're only going to put in the list items which they receive from at least 2 governments. But that's also a question. And the main thing that people didn't like is that it's a first crack in the dam. So far, companies did not search on our devices for the purpose of law enforcement. This is the first place where this is happening. It's only happening as part of the upload process for items that we upload, but the public didn't like this. Okay, so these are relevant papers. So the story is that Apple suggested this, there was a huge outcry, and then a few months later, they somehow rolled back. They didn't, these things disappeared from Apple's website, and they don't talk anymore about the system. These links still work, so if you want to recover the technical descriptions that Apple put, you can recover these documents. This is the description that I put, which is a bit more technical than the talk I gave here. And that's about it. And this is the case of PSI with specific requirements about how you do it. You do it image by image, etc. You need to do threshold solution, which I haven't seen before. You have a solution which is also based on random self-reducibility, and which I also haven't seen before. It's it's a very nice system. The whole picture is very complicated. So, any more questions?
Okay, several questions, but we'll just pick a few.
I can also I'll answer on the Slack afterwards.
Right. So one is, can you use something like Bloom filters to avoid dropping of hashes? This is with regard to the Cuckoo.
Yeah.
And
so,
yeah.
Okay. So yeah. So basically, you want to use the base system you have, the best encoding you have. You can use. I think that the best solution is cuckoo hashing with 3 where you look at 3 locations. I think that they could have potentially improved a little the storage that they use. But the important thing here is that just observing for this specific application, they don't care about dropping part of the server's input, because they don't care about dropping part of the database of bad items. That's that's the most important thing for me there. But also in general, usually Bloom filters are less efficient than cuckoo hashing. I don't recall a single example where Bloom filters were better. So I think that from a technical perspective, cuckoo hashing are, at least my experience is that it's better. Yeah.
Okay, so another one is, why upload dummy shares instead of just uploading nothing when the number of matches is below 30?
Okay, so the issue is, Apple, whenever I don't, but whenever someone sees some images, they can decrypt and they see that they get a share. Now, suppose they see that someone had 29 shares. They cannot decrypt what that person uploaded, but we know that this is probably not a good guy. So the government can come to them and tell them, whoever, for which you can decrypt more than 25 shares, we want to talk with that guy. Okay? And Apple don't want this to happen. So what happens, all phones, even, phones of complete saints, okay, which is like 99.99% of the population, will upload dummy shares. A random number of them according to some distribution. So I upload 80 shares, you upload 75, someone else uploads 90, and before, among these 90 shares, 30 are true shares, they won't be able to decrypt. So it will be hard for them to distinguish between phones of random innocent people and phones of people who had 29 shares. Now, it's not really that simple, because my phone is going to upload a certain number of dummy shares, and the phone of a bad guy is going to upload something according to the same distribution, plus 29. So his phone will upload more shares than mine, but still we have some doubt, which hopefully will be enough. Yeah. One more thing I want to say about this, it would have been nice for them to prove something about differential privacy that they provided, but they didn't prove anything. So I suspect that it's very hard to prove it, because otherwise they would have done it. But I don't know any information. Yeah.
Okay, we'll take just one last question. Would an homomorphic encryption based solution that runs on a remote server be better accepted than an on-device scanning system?
Yeah, so I think what's important here, so that would have been nice. I mean, I'm maybe not very efficient. So if I get it right, it's like a proxy. When I upload things, they go through a proxy and they are scanned over there. And I'm assured that they don't scan anything on my phone, just when I upload it. And Apple cannot see the images. That would have been maybe a better solution, probably not efficient. Right now, they only implement this as part of the upload process, but I have trust them to do that. So that would have been good, but it might not be very efficient. Okay.
Well, there are a bunch of questions more, but then I guess we should stop here.
So I'll go to the Slack channel after the second lecture.
Okay, thank you very much, Benny. We will resume after the break for the second talk about private sector section.
Okay.
Everyone, and welcome to the second talk about private set intersection, is given by Benny Pincus. Benny, please.
Hi, thank you. So in this hour, I'm going to talk about malicious security and also about amplifying the success probability. And also I'll have some conclusion at the end about PSI, which like trying to summarize many protocols from many papers. And I must say that many of the slides in this talk were written by my co-authors in different papers. Okay, so in the previous hour, we discussed about PSI based on OPRF, but the setting is like this. One party has, so here now it's going to be Alice, not Bob. She has an OPRF key that only she knows. Okay, only she knows the key. Okay, only Alice, not Bob. And then for each input of Bob, they run the OPRF, where Bob learns the output of the pseudo-random function f with this key on Bob's inputs. And then Alice sends, this is going to be Alice, these are Alice's inputs, she sends to Bob the output of the PRF on her inputs, and he compares. Now, for this to be efficient, we want the OPRF to be the most efficient. So we want to use pseudo-random function, which is the most efficient to implement. Okay? And apparently the most efficient OPRF constructions are based on OT extension, or these days on Volley. And the caveat is that they are secure as long as we implement them at most once, as long as we compute them at most once, as long as the party which doesn't have the key learns only single output. So you can think about a function like this. It might not be this specific function, and the keys are A and B. If you learn A times X plus B, it looks random. If you learn two values, then you can start computing the output on other inputs. Okay, so it's going to be very efficient, but you can only compute the function once. So obviously you cannot use the same function for all items. And the question is, which items of Bob to compare to which items of Alice. And if we're not too smart, we're going to end up with n-squared comparisons, which is not going to be efficient. So the basic idea is to use hashing. Okay, so suppose both of them use the same public hash function, they both know it, that map items to bins, say n items to n bins. So obviously, if both Alice and Bob have this blue item, they're going to hash it to a bin using the same hash function. So they're going to put it in the same bin. So therefore, what they have to do is to run an independent PSI for each bin. One PSI here, one PSI here, etc. Okay, so we end up with many small PSI problems, like n PSI problems. And if luckily Bob only has a single item in each bin, Bob or Alice, he only needs to evaluate the OPRF once, not more than once. Okay, so then we can use these very efficient OPRFs. The problem is that if we use simple hashing, n items to n bins, many bins are going to have more than one item in them. Actually, with very high probability, one bin will have log n items. So we say, okay, let's map n items to two n bins. You're going to still have this property as long as you're mapping to some order of n number of bins. Okay, so we need to do better. So the way we do better, since early papers on PSI, is to use cuckoo hashing using two hash functions. So for those of you who don't know cuckoo hashing, you should learn about cuckoo hashing. They should teach it in basic algorithms courses. And it works like this. You have two hash functions that mapping items to bins, not just one. So you map n items to something like 2 plus epsilon n bins, and each bin stores at most one item. So the thing is, each item is mapped to two potential bins, and you store it in just one of these two bins. So if x is mapped, say, h1 of x is this bin, h2 of x is this bin, you can store h in any one of these two bins, okay? When you look for x, you're going to look it in these two bins. And if y is mapped to this bin as this bin, you're going to look for y in each of these two bins. And so lookup requires two lookups, which is less good than one lookup. But the nice thing is this succeeds with very high probability. Okay, so there's a paper showing that that result showing that if you map n items to slightly more than 2n bins, and you also have a small stash, then with very good probability, each item is going to be mapped to either h1 of x or h2 of x, or it can be found in the stash. And the stash can be very small. So a stash of size s items in the stash, ensures a failure probability of n minus s plus 1. So a stash of only size 2 ensures a failure probability of n to the minus 3, which is great. So basically, you map n items to 2 plus epsilon times n locations plus 2 more locations in the stash, and you get like cubic failure probability. So this is great. And we can ensure that Bob has just one item in each bin. Now, we cannot have both Alice and Bob use cuckoo hashing, because then Bob might put X here and Alice will put X here, and they won't be able to compare to each other. So the way we use cuckoo hashing in PSI is the following. We have these two hash functions. Alice uses simple hashing. So she puts each item of her both with location h1 of x and in location h2 of x. Bob uses cuckoo hashing, so he puts each item either in h1 or in location h2. Okay, so Alice is going to end up with very fat bins with more than one item in each bin, but Bob is going to have just one item in each bin. Okay, so then for each bin, they can do this comparison, and Bob has a single item. So they can use this single usage OPRF, this very efficient OPRF. And Bob might have a few items here in the stash, and handling the stash, it's a complete headache, so we'll just ignore it now, okay? So this is basically how we use the efficient OPRFs for PSI. So in each bin, Bob uses cuckoo hashing. I'm just recalling the previous slide. He has one item. Alice simple hashing, so she has order of log n items. In each bin, they run an OT-based OPRF. Bob's learned this output. Alice computes F on all of her inputs in that bin. Alice sends to Bob the list of the outputs of F for all of the bins, and Bob compares them to what he learned. So is this secure against malicious adversaries? So apparently it is secure except for one simple problem, okay? So we can do the OPRF to be secure against malicious adversaries. There's one simple problem. Suppose both Alice and Bob have a value Z. Bob uses cuckoo hashing. So he puts Z either in H1 of Z or H2 of Z. Alice should put Z in both locations. Now, suppose that Alice is corrupt and she puts Z only in H1 of Z. Now, if Bob chose to put Z in H1 of Z, then Z will be in the intersection. If Bob didn't choose to put Z in H1 of Z, put it in H2 of Z, then Z will not be the intersection. Okay? So, okay. The problem is that Bob's decision about where to put Z depends on his other inputs. Okay? So basically, the fact whether Z is intersection or not depends on Bob's other inputs, even those which are not in the intersection, and leaks information to Alice about them. Very little information, but leaks information about them. And this, solving this seems inevitable, this seems like an inevitable problem with cuckoo hashing because we put an item either here or there. And the choice depends on other items. There's no way to go around it. This is how cuckoo hashing works. So Alice, by acting like this, might learn something about Bob's inputs. Okay. So any questions up to here?
No questions so far.
Okay, so we try to solve this problem. So, okay, what about the function that we're going to implement? So a very efficient function we can use is an OPRF that can be used once by Oru, Orsini, and Peter Scholl. And it's very efficient. It's secure against malicious behaviors. This is what we need if we want to have malicious security. And each table entry, the receiver Bob learns fi of x. So for row I of the table, he learns fi of x. And the sender can compute fi on all other inputs. So this is great. And the function has another property, which we didn't require earlier, but it's going to become very useful. It has a homomorphic property. So fi is the function we're going to use for entry I in the table. So if you take fi of x and fj of y, we're going to get f with the key, which is the sum of the keys of I and j, applied to x plus y, x XOR y. Okay? So this homomorphic property seems to be, it's unclear how to use it. But basically, when we apply the function to two different rows, if we sum the values we get this double homomorphic property. The function is applied to the XOR of the values in the two rows, and the key is the sum of the keys in the two rows. Okay? So how are we going to use this? Okay? So what I described, I write it here. It's based on the following papers. The function is described in this paper by Oro, Osin, and Peter Scholl. And the PSI applications are in these papers of me, Michael Sulek, Nitriu, Avishai Yanai, and Gayatri Garimela. Okay, so we're going to use something which is similar to cuckoo hashing, but not exactly cuckoo hashing. So Bob is using two hash functions, as is cuckoo hashing. And suppose that x is mapped to age 1 of x, which is I, and age 2 of x, which is j. So Bob doesn't put x either here or there, but he puts here two locations, v1 and say vi and vj, so that the XOR of these two inputs is equal to x. So it's unclear how to do that. It's not clear if this is possible. But he puts two values so that the XOR of the two values is equal to x. So instead of putting x in one of the two locations, somehow the combination of these two locations is equal to x. Okay? So for those who know, this is similar to garbled Bloom filters. You can also call this garbled cuckoo hashing. So this is what we want to achieve here. Okay, so suppose we achieve this. In the PSI protocol, Bob will run the OPRF here, and here he'll evaluate the OPRF with key I of Alice on his input here, VI, and here we'll compute FJ of VJ. And here is where the homomorphic property is useful, because if Bob sums these two values, he gets F with the keys I plus J of the X of what he put here. So what did Bob put in these two locations? He put two values whose XOR is equal to X. So basically what Bob learns is F of X with the key, which is the sum of the keys of the two table entries to which X could have been mapped. Now Alice, she knows what's the hash function. She knows that for each input of her to which two locations it could have been mapped. She knows the keys there. So she can compute this for each of her inputs. And then she sends this list, and Bob can compare this to his values. And what's nice here is that the attack that we said before, which is you should believe me, it's the only meaningful attack that we couldn't protect against before, of Alice putting a value either here or here, okay? The attack doesn't work anymore. Because what Alice sends to Bob is not f of this plus f of this. She sends to him a value which is the sum of what you get here and here. So she cannot identify whether Bob put his x here or here, because Bob is going to put x in both locations. Okay, so this needs a proof, but you can prove that Alice cannot. This provides security against malicious behavior. The only question is, how can we ensure that this is, how does Bob do this magic, this mapping into the table? So, any questions till here?
No.
Okay. Okay. So let's see. Suppose this is the table. And basically, Bob has a key, a value, and he wants to put a value in the table. Say he has We said X, and we said, okay, here we said that Bob will put X in these locations. In a general case, he has some key and he wants to put some value associated with the key. So, okay, suppose A is mapped to these two locations. He needs to put here two values whose occlusive O is equal to the value of A. That's easy. Okay, but the problem is that we have many such requirements and they might be conflicting. So how do we solve these requirements? So one option is to solve a system of linear equations. It's unclear whether they're solvable or not, but also solving a system of linear equations is very costly. So luckily here, we have a simple procedure, linear time procedure, which works like this. Suppose we have 4 items, and each of them is mapped to 2 locations in the table, and we need that the x of S1 and S5 is equal to the value of B, x of S3 and S5 is equal to the value of previously with A, here the value of B, value of C, value of D. We have all this restriction. So what we do, we recursively find slots which are constrained by just one key. So each key is an edge, and then basically it constrains these 2 values to have an exclusive O, which is equal to the value of A. Now, suppose we look at C and we say, okay, this slot, okay, this node has only one edge going into it. So there's only one constraint on it. The value of S2 XOR the value of S4 should satisfy the value of C. So basically, we don't care about this constraint anymore. We can fill the entire table with values. After we fill everything with values except for S2, we'll just, we already put something in S4. We'll put in S2 something so that the XOR of S2 and S4 will be equal to C. So since we only have one constraint, we have a node or location in the table to which we get only one edge. We can remove this because we'll fill the entire table with values. At the end, we're going to fill this, this table entry. It's going to be fine. Now, once we remove this constraint, then this entry, which previously had 2 constraints, has only 1 constraint. So now we can say, okay, about this S4, now it has 1 constraint. So we can leave it to the end, because after we fill the entire table, okay, the entire remaining table, we'll have some value at S1, and then we'll put in S4 a value so that S1 XOR S1 XOR S4 is equal to D. So we can remove this. So there we can, keep removing edges from the table. We basically, whenever we have a table entry to which there's only one constraint, one edge going into it, we can remove it from the table and handle the rest of the table. So this is great. After we finish all of this, we can start filling up. So we put here in S1, S5, 2 values that satisfy the XOR is the value of A. And then we put here, this is already fixed, so we put here a value so that the XOR of these 2 is the value of B, etc. So this is like a recursive procedure. It works well, and it works in linear time. Okay. And this process is called peeling. Okay, it's people in databases invented it. Basically, you peel the requirements from the table, you get to a core, and then you put the peels back. Okay, the question is whether this always works. Okay, so sometimes it doesn't work. So look at this graph here. Okay, suppose this is what hashing gave us. So after we did peeling, we end up with this subgraph. And here, each table has 2 constraints. Okay, the graph, if you look at this as a graph, each node has a degree of 2 or more. There's no node with degree 1. And basically, here we cannot continue with peeling because the peeling required that there will be a table entry with only 1 constraint, a node with degree 1, and here there's no such node. So basically what we have here, if we started from the large graph, we removed edges until we ended up with something which is called the 2 core. So the 2 core of a graph is the maximum subgraph where each node has a degree at least 2. Thinking of it differently, starting from a graph, it's the subgraph which contains all cycles and all paths between cycles. Okay, and here we cannot do peeling anymore. And basically, if we start from the this big table, and we can look at the table as a graph. So these are the nodes, and these are edges. We can run the peeling until we get to this subgraph, which is the 2-core, and then we cannot do peeling anymore. Then we're stuck. And the question is whether we're going to end up with this 2-core, how big it is, and what should we do about it. So there's a theorem, okay, from graph theory, showing that for a cuckoo graph, so basically the cuckoo graph is the one where this graph, you have a set of nodes, and each edge connects to random nodes. And cuckoo means that you have like 2 plus epsilon n nodes, and we have n edges, n constraints. Each item that you want to map to the cuckoo graph is mapped to two locations. So for these types of graphs of size linear and n, with high probability, the size of the 2-core is going to be only order of log n. Okay? In other words, we can do the peeling, which is great, until we end up with a subgraph of size order of log n. And then handling all log n should be easy because it's very similar. Even if you have a protocol, we solve this with quadratic overhead, cubic overhead, it doesn't matter. It's polylog. Okay? So actually, it is easy to solve it. Well, not easy, but you can solve it. You must somehow handle the 2-core while hiding which items are in it, but it's possible to do it. Okay. Okay. I'm not going to describe in detail how we're going to handle the 2-core. The question is how big it is. I have a slide which describes the entire protocol, but I won't go into details. If you're interested, you can look at the paper. The question is, what is this size of this 2-core? So looking at this, what do we actually need here? Basically, we wanted to store items in a cuckoo table, cuckoo hash table, but we wanted to hide which items we store. So basically, Bob, for each of his values, he wanted to put in this cuckoo table. I can go all the way. I won't go all the way back. Put, an OpenRef invocation for that value, but he should hide which value is mapped to each location, because this will leak information to Alice. So basically, we want an oblivious key value store. What's a key value store? Key value store, it's not something from cryptography. It's a database that lets you encode a set of keys and values, and then when you query with the key, you get the corresponding value. What's an oblivious key value store, which we call OKVS? It's something that we define, is where you hide the key. So you have this data set, and a query for an encoded key will return the corresponding value, and a query for a key which is not encoded will return a random value. And if the encoded values for the keys are random, then whoever does the queries cannot distinguish between them. So apparently, if you look at a whole set of modern PSI protocols, they all implicitly use this oblivious key value store. So this key value store, you have a set of keys and values, and basically what you want is a protocol where when you query for the keys, you get a value. When you get for something which you didn't encode, you get a don't care. And if these values are random or pseudo-random, this also looks pseudo-random, then whoever queries gets a value, but he doesn't know whether he received something which was encoded in the database or something which is totally random, because they all look pseudo-random. So this seems a bit odd, but I'll show you examples. Let me skip to an example first. So here's an example, then I'll go back, okay? So here's an example. I want to encode n values. You should be able to query about this, to query my encoding. If you ask one of these values, you get the right output. Otherwise, you're going to get something random, but you don't know whether you got something I encoded or not. So here's the way for me to do it. I can encode these values as a polynomial. So I have n pairs of keys and values. I'm going to interpolate the polynomial through them, polynomial of degree n minus 1. And this is the polynomial. Okay. My encoding will be the coefficients of the polynomial. when you want to read a value, you're going to evaluate this polynomial. When you want to read a value associated with a key, you're going to evaluate this polynomial on that key. If it's one of the values I put, you're going to get the value that I put in this data structure. If you get a query another value, you're going to get whatever the polynomial puts there, gives for that value. If the values are encoded as I encoded are random, then everything that you get from the polynomial is going to be random, just going to see a random polynomial. And the nice property here is that when you see a polynomial, you don't know which values are used to interpolate it. So I interpolate it based on keys and values. The values are random. So this doesn't give you any information about the keys I used. Okay. So this is an oblivious key value store. I would like to use oblivious key value stores, but more efficient. So let me go back. So the properties I would like to get, first, I want this key value store to be linear. Okay. So the decoding function will take some linear function of this long table. Even better to get a binary one where I just get 0-1 combinations. So what I described previously with peeling, okay, it's a binary OKVS. I take two entries in the table and I XOR them. What I described about the polynomial, it's also a linear OKVS to take a random combination of the entries. Okay, and actually this linearity property is a must for all the PSI constructions. So you can look at like this is the key value store, and for each entry you get some set of coefficients. You multiply them by the key value store, and you get the value. Now, what are the efficiency measures? First, we want the key value store to be as close as possible in size to the number of items. So hopefully M is as close as possible to N. And of course, there's the encoding time and the decoding time. So for the peeling process, the encoding, except for the 2 core, is linear. That's great. And the decoding, we just look at 2 items. For the peeling, this is the peeling. It's for a system we call Paxos. The memory, the size of the table was linear. Encoding and decoding were linear. That's great. However, they had that small, big problem that we couldn't encode all items there. Okay, because once we got to the 2 core, we got stuck. The polynomial I described, in terms of size, is optimal. To encode n items, I need a polynomial of degree n-1 with n coefficients. The size is as large as the number of items I want to encode. That's great. However, encoding and decoding take me a lot of time because I need to interpolate a polynomial. Another option is, instead of polynomial, encode using a random matrix. So each item I have will be mapped using a hash function to a series of coefficients for the table I use for the encoding. And if I want to encode a certain set of items, they're going to define a set of linear equations that this table has to satisfy. And then I have to solve these linear equations to find which items to put, what to store in the table. Okay. So the size is going to be linear. That's great. But the encoding and decoding, they require me to solve systems of linear equations. And I might also have here linear equations which, I get a system which I cannot solve. But since this is random, this happens with small probability. If it's over a field, then the probability is basically f to the power of the difference between the number of rows and columns. And if it's binary, then all entries are 0 and 1. So by adding an additional lambda gates, the probability is going to be 2 to the minus lambda. So questions up to here?
No.
Okay. So, I'll continue a bit with this construction. Then there's going to be a, turn. Okay. So suppose I know in advance that the 2 core is going to be of size up to order of log n. Okay. And this I know from, graph theory or, analysis of random graphs. Then I can encode these log n items using a less efficient OKVS. So even if I use a random matrix, which will cost me quadratic time to encode, it's only quadratic in log n, okay? So in total, encoding these, say, using a quadratic, random binary matrix will require very few variables. And encoding will take cubic time, sorry, but it's cubic in log n plus lambda, so it's all going to be efficient. And the total size is going to be linear in n plus linear in log n plus lambda. Now, this is, okay, I still have to hide which items are encoded in the big table with peeling, which items are encoded in the small table. This is a bit tricky. It's all described here and in the paper. This thing I'm not going to describe, okay? You can read this. The big problem is what's hidden inside this O notation, okay? And the problem is not that we know that these constants are very hard. The problem is that we don't know what these constants are, okay? If we look at the theorem that ensured us that the size is going to be order of log n, it's all asymptotic. If you, very hardworking, start looking at the proof and try to find what are the constants in these asymptotics, you get to other statements in probability, which also has an asymptotic in them, okay? And then it's like, it seems very hard to find what are the constants are. So this is, what's missing. Okay, so the problem is, this great system, I want to implement it. Okay, and I have this theorem, and I know that if the size of the two core is order of log n except with probability epsilon, then I can use a table of size order of log n plus order of log n plus lambda, and it's going to be successful. And the failure probability is epsilon by 2 to the minus lambda. That's great. Okay. What should be, what are the constants here? Okay. So in this PRTY table, we use some heuristics. And based on the heuristics, we found out that if the table size is 2.4n, then the failure probability seems to be 2 to the minus 40. But the elephant in the room, essentially for almost all previous PSI results that use cuckoo hashing, is a rigorous analysis to translate the asymptotic theorem to concrete parameters, okay? And this is like a huge problem, okay? So what we want to achieve is something like this. There's a very nice result from last year showing that 3 cuckoo hashing, if you map items with 3 hash functions to a table of size 1.23n, you succeed with very high probability asymptotically, okay? Now we want to find, we want to implement this, okay? So suppose we want the failure probability to be this. We want to use this construction. I want to map 1 million keys. They say, 1.23, I want to use 1.3 million, just to be on the safe side. Will this ensure me that this succeeds with at most 10 keys in the 2 core? I look in the theorem, you cannot find it from the theorem or from the proof. It's, it seems extremely hard to identify the constants there. So one might say, okay, let's run a simulation to find what's, whether you get this small failure probability. The problem is that if you want to run a simulation to verify a 2 to the minus 40 failure probability, you have to run at least 2 to the power of 40 experiments, okay? And this is 1,000 billion experiments, each one of them running a million items. It's a huge cost. Once we did it with Christian Weinert and Thomas Schneider, and there they had a cluster where they run more than 2 million core hours to do the simulation. But you cannot do it for each system that you build, okay? And what if we need 2 to the minus 80 failure probability? Again, that would be impossible even with the strongest cluster to verify experimentally. And this happens for many construction of PSI. We use hashing. It's a probabilistic process, sometimes it fails. When we use hashing, say, for caching in operating system, then if you have a failure, the system runs a bit slower. If this happens 1 in 1,000 cases, it's not a big deal. In PSI, each hashing failure results in either inaccurate output or information leakage, which is something that we don't want to have. Now, there are places where maybe we don't care about inaccurate outputs. The system application I told you about, we don't care about false negatives because we can just compare to, say, 90% of the CSAM database, that's fine. In machine learning, they don't care about approximations. But in general, when we're talking about PSI, we want an exact output because otherwise there's a privacy leakage. So we have a problem because all of these, great hashing techniques, cuckoo hashing, etc., the people who designed them, all the results are asymptotic without any concrete bounds on failure probability and on sizes. And we need these concrete bounds if we want to implement. So for theoretical analysis, we want to have a negligible failure probability, smaller than any polynomial. For concrete analysis, we want the probability to be, say, below 2 to the minus 40. So when you run experiments with cuckoo hashing, it's very good at, we see very sharp threshold. If we have this, bound of 1.23, if you run an experiment, you see that the threshold goes like, this when you run it. That's great, okay? But when you want to specify, how big should the table to be to have a 2 to the minus 40 failure probability, you have to run a lot of experiments, which are very costly. So you can either work heuristically, you can either run experiments, and that's a new system that we going to describe here. We can work with amplification. So one thing to note before using amplification, okay? The good side is that cuckoo hashing, the construction, they have very sharp threshold. Table is a bit above the threshold, and it seems to always succeed. So for practical applications, this should be fine. But if you want to verify the failure probability, there's no theorem that can help you do that. One thing that you should note, and that's a cautionary tale, okay? The failure probability is a function of the input size. It's something like, n to the minus 3. This means that for larger inputs, you're going to have very low failure probability. For smaller inputs, cuckoo hashing is going to fail more often. Okay? So if you're using smaller inputs, you should be more careful. Or you should use less efficient PSI because you don't care, because the inputs are small. But these hashing techniques, they don't work for small input sizes. Okay, so the new approach is amplification. We cannot run an experiment to verify failure probability of 2 to the minus 40, but we can efficiently verify statements about large failure probability. Okay, so if, say, I want to say that a certain scheme maps, say 1,000 keys into 1,300 bins, with a very small 2 core, and I claim that the failure probability is smaller than 2 to the minus 15, then this I can verify by running, say, 1 million experiments on my laptop. So verifying a large failure probability is rather easy. What is hard for me is to experimentally verify a small failure probability. So the main idea will take smaller OKVS instances for which we have large failure probabilities, which we can empirically verify using experiments, and we will compose them into an OKVS for many items, and we will prove that the large one has a small failure probability, like 2 to the minus 40. So we take components that you can verify using very efficient experiments and build a large component for which we can prove a small failure probability based on the experiments. Questions?
No questions.
No. Okay. Actually, I can see you, so you can raise your hand, and then I'll answer. Okay. So here's the construction. So we could call it a star, but it doesn't look like a star. They should be around this guy. Okay, say we're going to have 4 OKVS instances, 4 hash tables, each large enough to store 1/3 of the items. So basically, the total size is like, 4/3 times n. So it's going to be larger than n. And each one of them is large enough to store n over 3 items with the failure probability p. So p is going to be like 2 to the minus 15 or something like this. These are fewer items, so we can verify this using experiments. And we want the whole construction to have a failure probability of, say, p squared, which is like going to be 2 to the minus 30. And so, okay, so we're going to have a hash function which maps an item to one of these T1, T2, T3, these 3 tables on the bottom, not to the one on top. Okay, and each one can store 1/3 of the items. So how are we going to decode? So we have a key and we want to read the value from the table. What we're going to do, the hash table, the hash age is going to map the key to one of the 3 tables down here. So we're going to decode from this table. Say the item is mapped to this table. We're going to decode from this table whatever it tells us about the key K. We're going to decode from T0 whatever T0 tells us about the key K. And we're going to XOR the 2, and this is the result. So basically, when we want to decode K, we go to the table on the bottom to which K is mapped, decode what it tells us about K, go to the top table, decode what it tells us about K, and we XOR the 2 results. So this is how we decode. The question is how we put items there that things work. So here's the encoding. Now note that I'm talking about mapping a set of n over 3 keys to a table. We put keys and values associated with them in the table, but the success of the encoding only depends on the keys. The keys define to which entries in the table each item goes. After, if we can map the keys into the table, we can put there any values that we want to be retrieved by these keys. But the success only depends on the keys before we know the values. Okay? So the first thing that is good is if encoding succeeds for all of these 3. So it only phases probability p, so probability 1 minus p to the power 3, it succeeds for all of these 3 tables in the bottom. Okay? And then what are we going to do? So first, in the top table, we're going to put random values. We don't care about it. And then for the bottom tables, say for this table, each item which is mapped to T1, we know that in the coding, we're going to read something from it from T1, we read something from T0, and we're going to XOR. We already put in T0 random values. We're going to know what K is going to retrieve from T0. So we're going to put for K in T1 exactly the thing that, when we XOR it, what we retrieve from T0 will give us the right value for K. And the same for T2 and T3. So basically, first we encode it in the top, and only then we encode in the bottom. Okay? And we can put any values that we want. Now, suppose that it happens that the encoding succeeds for the keys mapped to T1 and T2, but for T3 it doesn't succeed. Okay, for T3, the set of keys that are mapped to it, we cannot, they don't map, we end up with a large 2-core, whatever, it doesn't happen. So the way we work is like this. First, we put random values here. Now, we know that the values that are going to be mapped to T3, the way we're going to decode them, we're going to read something from T3, retrieve the information associated with them in T0, and XOR the 2. Now, for T0, the encoding succeeds. Okay, so we're going to put in T0 values so that for the items mapped to T3, the XOR of what we put for them in T3, which is completely random, and what we put for them in T0, the XOR is going to be what we should encode for them. And now, after we put values in T0, we still need to take care of the items mapped to T1 and T2. So we're going to put in T1 values so that the XOR for the items map to T1, the X of what we put here, and what's already here will give us the right decoding. And the same in T2. Okay, so basically we start from the table in the bottom that we failed to map to. We put the random values. Here we put values which fixed encoding to the items that are mapped both here and here. And here we put values with fixed encoding for the items mapped here and here. And of course, we can do the same if the encoding fails for T1, but not for T2, T3, and T0, or it fails only for T2. So basically what we got here, the previous slide, was a system that works if the encoding fails for at most one table. If the encoding fails for two tables, say for these two, then the procedure I described doesn't work. But the probability that encoding fails for two tables, okay, is, choose 2 times P3 plus the probability of failure for 3 tables, etc., but it's much smaller, okay? So basically, we ran experiments verifying a failure probability of P, and we get that the failure probability for the whole system is 6 times P squared, so it's much smaller, okay? And the size is 4/3 times the size of an optimal OKVS for an item. So it's 4 times an optimal OKVS for 1/3 of the items. And in order to know, what parameters to put here, we need to verify a rather large failure probability, P. And we get a smaller failure probability of P squared. And here I used 3 tables in the bottom to make things simpler, but you can generalize it to any number of bins. So this is one example we used. So we start from 1 million items. We have at the bottom 160 bins. So on average, each bin is going to have 6,250 items mapped to it, but we make each bin this large. Why did we make it this large? Because we ran experiments on these small bins, verifying a failure probability of something like 2 to the minus 5, 15 to the minus 20, which is very easy to verify. And based on a theorem, just analyzing what's the probability of 2 of them failing, we get that the failure probability for the entire system is 2 to the minus 45. Okay? And the encoding is very efficient, and the total size is 1.388 times n. Okay? So overall, we get something which is it's linear, and it's very close to n. And the total, and we can experimentally verify a very small failure probability, even though we only we can just work with a laptop and verify this. So this is the amplification of the failure probability. Now, we can design recursive construction and somehow try to push this further. For practical systems, it seems that this single level I described is sufficient. The open question, which I don't know how to solve, but maybe it's solvable, it would be very nice to start from a polynomial size OKVS, which has a polynomial small failure probability. So if you recall, cuckoo hashing has a failure probability of n to n minus s, where s is the size of the stash. So we start from polynomial failure probability. And somehow I would like to take polynomially many such small OKVSs, combine them, and get something with negligible failure probability. Because all the tricks I describe here, we start from polynomial failure probability, we end up with polynomial failure probability. Much smaller, and this is all that we need for practical applications. Getting to negligible failure probability, that would be very nice. Yeah, I thought about it quite a bit. I don't know how to do it, but it might be possible. And okay, this OKVS, okay, huge sets of, almost all recent PSI papers use this construction. Okay, and by this amplification, we basically move from heuristics to rigorous construction. The heuristics works. I'm pretty sure it's fine. But here we can prove things using experiments. The main takeaway, okay, ignore everything. The main takeaway is that we get malicious PSI with runtime, which is similar or even better than the previous PSIs with only semi-honest security. So PSI is a great example where malicious security gets you almost the same. We get it with almost the same overhead. Okay, as semi-honest. Okay, so questions up to here? Okay, so what I want to do in the last 10 minutes is a quick recap of the big PSI picture. Okay, so suppose we need to implement PSI, what should we be using? Okay, simplicity. Okay, this is something which is not described in papers. In papers, actually, many times you want techniques which are very cool and interesting, etc. Okay, and we want to optimize performance. If you really want to build it, you want a simple solution. Well, first of all, okay, for you to understand, for you to implement, and this Diffie-Hellman-based solution is extremely simple, and also to explain this to your managers or customers. Okay, you don't want to go tell them simplification, cuckoo hashing, whatever, expander graphs. This is something they can understand. And this is extremely important, okay? And these Diffie-Hellman constructions are much simpler than others. So that's a great property of them. Also, we're using probabilistic constructions. As I said, if you want concrete fair probabilities, sometimes a heuristic is fine. Sometimes we can have hashing failures, say for machine learning or for CSAM detection. If you want to have a rigorous analysis, it's quite complicated. What we should remember, I'm talking here about someone who wants to implement this, the fair probability decreases with the input size. If you work in with small input sizes, make sure that the failure probability of your system is still small, because it might be much larger, because 1/n is not that small where n is small. Okay. What input size should I plan for? So, okay. The cool hashing, the cool PSI systems with the best performance work well for larger inputs, because we use OT extension or Vole, which have a pre-processing phase, which doesn't, if you have a small input, it doesn't make sense to use it. Okay. Also, the hashing failure is smaller for larger input set. If you have smaller input set, then the hashing failure is large. So the bottom line is that if you have smaller input sets, again, this Diffie-Hellman simple solution might be better than the more efficient protocols. For smaller input set, there's a recent Diffie-Hellman-based protocol of Mike Kusulek and E3U, which were co-authors on the best papers for OT-based PSI. And okay, and this is the OT-based PSI performance. This is the Diffie-Hellman protocol that they designed, a bit different than the one I described. And this is the input size. And they implemented both, and these are now their protocols, both this and this. And the Diffie-Hellman one is better for smaller input sizes. Okay? Because all this strong machinery, Vole, OT extension, etc., doesn't kick in until your input size is, say, 1,000 items or more. How to measure performance? What's more important? Communication or computation? Okay, what's more important? So Google, in their paper, they say, whatever, communication costs are far more important, because they can, in the data center, they can put as many cores that they require. The communication is the bottleneck. On the other hand, Apple, okay, remember each PSI message goes with a photo. The photo is 1,000 times larger than the PSI message. They don't care about communication. They do care about computation, because this translates to battery usage on the phone. So for that application, computation is more important. And in general, this is a paper we had. We said, okay, we both are important. Which one is more important? Let's try to compare them together. So let's compare dollars. So cloud service, AWS, they charge you something for CPU. They charge you for communication. These curves are curves which are equi-cost. You have the same cost spending this time of communication, this amount of computation, amount of communication and amount of computation here. So all points on this curve have the same cost. When you design a protocol, you want that the sum of the cost for communication or computation will be the smallest. So you want to be as close as possible to here. So here you can compare both of them together. Okay, do you want semi-honest security or malicious security? It depends on the application. But luckily for PSI, the performance gap is very small. Okay, so for Oblivious Transfer-based protocols, like the one I described to you with that saying that the Oblivious Transfer-based protocol, it's almost the same overhead. For the Diffie-Hellman-based protocols, then the recent one by Rosulik and Trio, the malicious one is only 20% lower than the semi-honest one. So to sum up, what should you use? After this slide, okay. So the Diffie-Hellman-based protocols, so the blue is good. They have the best performance for small inputs. They are very easy to implement and explain. You can modify to compute the intersection size very easily, but not to do many other things. The Oblivious Transfer-based protocols, they're much, much more efficient for larger inputs by orders of magnitude, but they're more complicated and they're harder to modify. And you can also look at combining PSI with generic MPC, and there you can compute any function that you want. That's the main advantage, not just the intersection, but any analysis of the values. But they are slower and they're more complicated. And yeah, so question? Yeah.
Okay, so we have a question about the previous lecture. So you mentioned in slide number 4 some applications to PSI. And the question is about the probabilistic analysis. And the question is, which protocols or real-life situation would fit that example?
With the probabilistic analysis. Okay. So actually, the Diffie-Hellman-based protocols, usually they're very... Okay. Why we needed the probabilistic analysis? Because we use cuckoo hashing and variants of it. Why did we use cuckoo hashing? Because it's better than hashing. Why did we use hashing? Because with Oblivious Transfer, we have very efficient OPRF protocol, very efficient pseudo-random functions that we can only evaluate once. When we use the Diffie-Hellman-based protocols, it's a function that you can evaluate many times. So you don't need hashing. So you don't have the problems that come up with this probabilistic analysis. When you use these OT-based protocols, which are efficient maybe by 3 orders of magnitude, definitely by 2, okay? You use pseudo-random functions that can only be evaluated once, and therefore you need hashing, and then you run into this probabilistic analysis problems. Yeah. Okay. So here we are, and something I did not describe is a completely different model for PSI, outsourced PSI. Suppose there are many parties, and they don't want to compute PSI themselves. Each one of them shares his or her input between, say, 3 servers. And then the servers will compute PSI between them. The intersection of kinds of analysis. So this is the completely different model. It's a different trust assumption. I don't trust myself. I trust that these servers do not collude, but the resulting protocols can be very efficient. And I think that's it.
Okay, Benny, thank you very much for 2 great talks on PSI. We're going to take a break now and resume with Peter's talk about the pseudo-random correlation journey. everyone, and welcome to the third talk of the morning session. This talk will be given by Peter Shaw, who's following Yuval's talk from yesterday's about PCGs, are going to show more advanced constructions. Please, Peter.
Thank you, Kamit. Yes, so I guess by now you've already seen quite a bit on vector OLE and PCGs over the last few days. So Yuval gave this very nice survey of the general area of various different constructions. So what I'm going to do today in this talk and the next one is dig a bit deeper into some of these. So firstly, in this talk, I'll be diving into the PCGs from LPN for Oblivious Transfer and vector OLE, getting into some of the details on the protocols involved, looking at performance numbers. And then for the next talk afterwards, I'll be looking at these PCF constructions, which Yuval briefly mentioned from number theoretic assumptions. Okay, so for the outline of this talk, I'm actually going to start by having a quick recap of the kind of classical approach to doing OT extension in this non-silent way, predating PCGs, because I think it's kind of relevant to understand and put in context for the more modern constructions, and it works in a slightly different way. So it's, I think, interesting to see the differences and perhaps use that as inspiration for future ideas. And then building on that, I'll present the silent OT construction, which Yuval gave yesterday, in a slightly different manner, in a little more detail, and giving it in some kind of somewhat general framework as to how we can build these PCG type things, which again is giving you the hope of understanding things in a different light and perhaps leading to different constructions one day in the future. Then I'll be looking at the setup protocol for generating the PCG seeds and how we achieve active security there, and concluding with some open problems, as usual. Okay, so I guess you've seen this slide quite a few times by now, so I won't go into the details because the motivation is MPC in this preprocessing model, and what we don't want to do is replace this expensive preprocessing phase with this much shorter setup phase, which just distributes a pair of short correlated seeds to the parties, which they can then silently expand in this silent preprocessing phase to get all of the correlated randomness they need for the online phase of the protocol. And eventually, this trusted setup functionality, which distributes the seeds, will be replaced by some small setup protocol, which again has low communication. Okay, and then formally, just to remind you of the definition, so PCG is tied to a specific kind of correlation, which we want to generate, given to here the two parties. And to do this, we have a pair of algorithms, the key generation algorithm, which just distributes the two PCG seeds, and then the expansion algorithm, which takes one of the seeds and outputs some correlated randomness. And the main security property we want from this is this notion of security against insider attacks, where if an adversary is given one of the keys, say here K0, then the other party's output, R1, coming from expand, should be indistinguishable from a freshly sampled output from the correlation conditioned on coming from the distribution, which have the same set of R0s coming from key K0. And this is enough to get the right kind of indistinguishability we need for secure protocols and can be plugged directly into many MPC protocols in the preprocessing model, for instance. Okay, so I'm going to focus on Oblivious Transfer in today's talk. Pretty much everything I'll talk about also applies to vector OLE. I'll sometimes mention the differences, but OT is a little bit simpler and easy to see. So the OT functionality is represented by this ideal box, this trusted party, which takes the two parties' private inputs. So Alice has a choice bit B, Bob has two strings, and Alice wants to get one of these strings, while Bob does not learn which string she received, and Alice doesn't learn anything about the other one, of course. So classically, we know that OT requires public key cryptography to build, and this is the kind of main drawback of standard OT constructions, is that this is very expensive, especially in situations where you want to do a lot of OTs. So the kind of thing to imagine is maybe a complex secure computation of a very large circuit where we might need millions and millions of OTs. So the idea of OT extension generally is to minimize this reliance on costly public key operations and shift this to maybe a one-time or small setup phase, while the rest of the OT extension can be carried out only using cheap symmetric cryptography. Okay, and a related notion is a variant of OT called correlated OT, which is defined for a batch of OTs. So here we have M OTs, where Bob is the sender, but this time, instead of choosing his strings independently, every pair of strings in the ith OT now has this correlation where the XOR to give this fixed difference delta. And this can also be seen as a kind of vector OLE. So there's subfield vector OLE, which I also mentioned in the talk on Sunday. And it's also equivalent to an information theoretic MAC over F2. So if you look at the receiver's output, then this is just SI plus its bit BI multiplied by the fixed offset delta, which is now chosen to be a lambda bit string for security parameter lambda. Okay, so correlated OT is useful because it's essentially all we need to build OT. It's got a kind of simpler structure with this fixed correlation, which makes it easier to build. And if you want to use this to get a general OT, then you can directly turn this correlated OT into random OT non-interactively using a hash function. So Bob will just take his pair of strings, so SI XOR with delta, put these through a hash function. This kind of breaks the correlation to find these two independent and random looking messages. And likewise, Alice can hash her output string YI and get one of Bob's two new strings. And if the original inputs to the correlated OT were random, then the security property of this hash function, if it's long as it satisfies this kind of pseudo-random correlation robust property, then the resulting random OT strings will be pseudo-random. And of course, once we have random OT, we can use that for our MPC with preprocessing and convert it to a chosen input OT in the online phase, for instance. Okay, so let's move on to the classic IKNP OT extension protocol, going back to 2003. So this construction, it's very simple and elegant. It relies on a nice symmetric property of correlated to OT. Basically has three steps I like to think of as a correlate, transpose, and hash. So first off, we start by creating a batch of correlated OTs. So here is kind of visually represented just a single correlated OT on a very long bit string. So Bob has a string S, which now is going to be very long, and S plus delta, where again delta is a very long bit string. And we'll create a batch of these, roughly security parameter of these, and put them all into the rows of a matrix. So now Bob has these two matrices, and Alice has a single matrix where each row is one row from one of Bob's two matrices. Okay, so this is the correlate phase, where we set up these initial batch of very long correlated OTs. And now in the transpose phase, we essentially want to transpose these matrices. So let's look at Alice's outputs here. So we have this YI matrix. And if we transpose it, we just turn it on its side, right? So maybe that's not so helpful. If we rename things a little bit, then we can look at this more clearly. So instead of looking at the columns of the matrix, we're now going to look at the rows, which were the columns of the previous matrix, indexed by superscripts here. And we look at this right-hand part especially. So each column was this choice bit B multiplied by this fixed offset delta. Then if we look at the rows, then that's actually equivalent to having a single bit of delta multiplied by this entire string B of Alice's choice bits. So this is kind of given us this symmetric property compared with what we started with on the left. So if we now think of the deltas as choice bits, then we have a new set of correlated OTs where the roles of the sender and receiver have actually been reversed. So we started off with, remember, this small batch of K OTs on very long strings, which means now by transposing, we've converted this into a large batch of MOTs on only k-bit strings. And then the key here is that if Alice chose her choice bits B to be uniformly random in the first place, then this can kind of take the place of the delta in a correlated OT, and we can directly apply the hash function to the transposed OTs to get a large batch of random OTs. So that's IKMP in a nutshell. Now, if you think about the efficiency of this, so this transposing and hashing, this is just completely non-interactive, a small amount of local computation. So the only part of this which is non-silent is creating these correlated OTs in the first place. Essentially, the communication is proportional to the length and the number of OTs. And for security parameter 128, you need 128 bits for each OT you want to output in the end. And this is what we want to avoid, of course. So for comparison, if you look at silent OT extension, I kind of think of this as being very similar steps, but now following a slightly different paradigm where we correlate, expand, and hash. So note that we're not going to do any transposition. So the roles of the two parties throughout the protocol will always stay as receiver and sender. And this correlate phase will, of course, have to be different because we don't want to communicate and send all of these bits to set up the OTs. So there'll be a kind of special, kind of smaller correlation that is set up to allow this silent expansion in the second phase. And the last part of the hashing is identical in both. So all we want to do is generate correlated OTs. Okay, so the rough goal then is just to take this set of correlated OTs we start with. This time they're not going to be on very long strings. They're just going to be, you know, the string length we want, and we only start with a few of them because we want to somehow magically expand these into a very large batch of correlated OTs where the new receiver bits are pseudo-random. So obviously, we need to apply some kind of cryptography here, right? We started with something small, expanded it to something large. So a natural thing to think about is, okay, what if we have a pseudo-random generator which satisfies some special homomorphic property which might preserve this correlation? Okay, so suppose there's a PRG which is linear. So G of S plus T is G of S plus G of T. Or here we want the addition of the outputs to be XOR, since we're working on bit strings. And then this actually works out. So the receiver can just take its bit strings B and expand them using a PRG to get a long vector of pseudo-random bits. And then the strings of the OT, these strings SI, YI, can be expanded in exactly the same way using a PRG. And the linearity means that we preserve the OT relation throughout this process. However, there is a slight problem with this process, which is that this kind of PRG does not exist. If you have any PRG which satisfies this completely linear relation on its outputs, then G will not be secure. You can easily break this using linear algebra. So we need to look for some kind of alternative. Now, one possibility I'll quickly mention is that you can build PRGs from lattice-based assumptions like LWE and ring LWE, which are not quite homomorphic, but they satisfy this almost additive homomorphic property with some small probability of error. And you can kind of make this work and get something which is not really the silent OT you want, but it's a kind of weaker flavor of the same type of thing, which I looked at in this paper from PKC a few years back. But it's not really very practical. It didn't seem to work out so great. So the right kind of PRG to use here actually seems to be to take a different assumption, which is where learning parity with noise comes in. Okay, so what is this LPN assumption? So we work out some modulus P, which can be 2 or can be larger. We have a public matrix A, multiplied by a secret S, and then add some random noise vector. The idea is that by adding this noise, we should make this somehow indistinguishable from the uniform distribution. It's hard to recover the secret of noise given this noisy encoding of S. Okay, but this actually also looks very similar to LWE, right? So with LWE, okay, normally we work with larger modulus, not just p equals 2. We have the secret S sampled uniformly over ZP. In LWE, this noise vector is usually chosen to be small relative to the side of P. So it's often some Gaussian distribution where each coordinate is fairly small, and that's what gives us the pseudo-randomness. So the only difference in LPN is the noise distribution, essentially. So instead of choosing E from some Gaussian distribution, we choose it to have a small Hamming weight. So we can either independently choose each coordinate from, say, the Bernoulli distribution for working mod 2 with some small error probability, or we can even fix the number of non-zero coordinates and then sample it uniformly subject to this. Okay, so so it turns out changing this error distribution just in this small way actually greatly changes the types of things you can build from this. So for instance, LWE, we can build fully homomorphic encryption. With LPN, we don't even know how to build additively homomorphic encryption. But on the other hand, this nice structure of the noise for LPN actually seems to make it much easier to work with for MPC type applications, as we see here. Okay, so from LPN, obviously we can't build linear PRGs, but we can build these PRGs which have this kind of almost linear property. So if you view the PRG seed as a seed having a special structure, so first this random secret S, and then this sparse noise vector, E, which obviously is a very long vector, but has low entropy, at least lower entropy than the output, then applying this linear transformation by multiplying S times A and adding the noise gives us something pseudo-random. And there's another construction called the dual construction, where we don't have a secret S. We just take the noise vector and then multiply that by a very long compressing matrix. And by compressing the noise with the right kind of matrix here, we can actually get something pseudo-random. And for H, which is chosen in a way related to the original A from LPN, this is equivalent to the same assumption. So both of these are secure PRGs under LPN. And of course, now we have this nice linear evaluation as long as we start with this error vector E as our input. So a quick note about the properties of these two constructions. So in the primal construction, because of the way you have to choose the parameters based on known attacks, we're limited to a quadratic stretch in terms of the entropy we end up with compared with what we started with. Whereas the dual construction, we don't have this secret anymore. And it turns out we can actually just increase the output length by scaling up the dimensions of the matrix. And we don't need to increase the noise weight of E proportionally. So the best known attack is essentially independent of the dimension and just scales with the number of non-zero coordinates in the error vector E. So we get an arbitrary polynomial stretch in this PRG, and so it tends to lead to better communication, but it's harder to implement because we have this very big matrix multiplication, which is much heavier to do computationally compared with the one in the primal construction. Okay, so how do we exploit this sparse noise from LPN to build the PCGs? So as you saw in Yuval's talk, the goal is to compress secret shares of some sparse vector. So here we can think of this as the correlated OT phase for the OT extension. Right. E is now going to be some sparse vector chosen by the receiver. Think of it as some initial sparse choice bits. And then delta is the sender's correlation in the correlated OT. And we want to uniformly expand this when we're given secret shares. So we can give out the secret shares in some special compressed way. Then we can expand these to get large shares of the product and then apply the linear transformation from LPN to get pseudo-random correlated OTs. So that's the essence of the LPN-based OT extension. Obviously, the main ingredient here that we need is to actually create these shares of the sparse vector. And we're going to do that using puncturable pseudo-random functions. So while Alette talked a lot about function secret sharing, and we've mentioned that we can use this to compress sparse vectors, for this case of silent OT, this is actually overkill, and you can get away with this simpler object of a puncturable PRF, which makes the constructions, I think, easier to understand and also easier to implement. So puncturable PRF is a standard pseudo-random function with a key generation algorithm, which allows evaluating the function on all inputs, as well as a special punctured key generation algorithm, which produces a punctured key programmed to be punctured at a specific point alpha. And given the punctured key, you can evaluate the function at all points in the domain, except for the point alpha. And for security, we require that when you're given this punctured key and alpha, then the missing evaluation, fk at alpha, is pseudo-random. Okay, and there's a very simple construction going back to the GGM-based construction of a PRF from a PRG based on a binary tree, where the punctured keys essentially have this logarithmic blow-up in size, where n is the size of the domain of the PRF. So given a puncturable PRF, we can share a sparse vector by first giving out a PRF key k to the sender, just chosen randomly, and then giving the receiver this special punctured key, punctured at a point alpha, where alpha is going to correspond to the, say, a non-zero coordinate in a vector we're sharing. I suppose we're just sharing a noise vector with weight 1. Okay, so then by just applying the PRF evaluation at every point in the domain, the sender obtains a pseudo-random vector of length n, while the receiver obtains the same vector, just missing this one evaluation, the position alpha, which it can't compute. So if we just XOR these things together, then we actually have shares of a sparse vector already, right? So at position alpha, we're going to get this pseudo-random value not known to the receiver, and the rest everywhere else, these vectors are shares of 0. So the only thing we're missing here is, okay, this kind of noise value at position alpha in the vector is this pseudo-random output of the PRF. So perhaps we also want to tweak this so that we can multiply this value delta, which is known to the sender. And this can be done easily by just giving out a correction value. So the receiver will also get from the setup phase fk of alpha masked with delta, and then can adjust its shares accordingly so that we end up with delta multiplied by a sparse vector. Right, so I think this is a very simple and natural approach for doing this from puncturable PRFs. And note that the sender just has to store a single key, which can be 128 bits. And the receiver has this punctured key, which has this log n overhead, but it's still only lambda times log n bits when we're expanding this to produce an n-bit vector. So this is an exponential compression from the original length of the vector. Okay, but this only gets us a single weight 1 vector, whereas what we want to use LPN is sparse vectors with many non-zero coordinates, say t, where t is related to the security parameter. Of course, the natural way you can do this is just by taking t of these weight 1 vectors and then adding them up after expanding the shares. But then you incur this factor t overhead in the computational cost of expansion, as well as the seed size. This can be improved by using cuckoo hashing, and you can make this computation actually linear, but it's kind of expensive to implement and add some overheads, which would be nice to avoid. So a different method, which I think is generally more preferred in practice, is to have a more structured error vector. So we can divide this error vector into fixed blocks, where each block has only a single non-zero coordinate. And then we can just use a batch of weight 1 vectors of a shorter length and concatenate them. And this gives us the optimal evaluation if each punctual PRF can be evaluated in linear time. So we get linear complexity overall for the entire weight t vector. Of course, the downside of this approach is that this regular error pattern gives us a slightly different assumption compared with standard LPN, which we may have to account for when choosing parameters. Okay, so there was one thing I haven't talked about much in the silent OT construction so far, which is how we actually plug in the LPN assumption. So of course we use punctual PRF to share these sparse vectors. And then in the primal case, we also need to share this secret key times by delta. Remember S is now some uniform vector, but of a smaller size. And this we can just do using correlated OT in the standard way. So that's fine. And once we have these, we can apply the linear LPN function to get our pseudo-random correlated OTs. And the question is, okay, which matrix do we choose? Do we want the primal one? Do we want the dual one? There's a lot of different choices here. So one thing you don't want to do is just choose a uniformly random matrix, because then based on the number of OTs we want, with millions of outputs eventually, then this matrix multiplication is totally impractical. So with the primal approach, one thing you can do is just choose this matrix A to be sparse. So for instance, it's common to choose it so that each row has only, say, a constant number of non-zero coordinates, maybe 10 in practice. So then you get a linear complexity of doing this matrix multiplication. And the security of this goes back to an assumption which was introduced by Leknovich in 2003, used for public key encryption. And well, I'm not sure it's been used a lot in practice, apart from with the silent OT constructions, but at least it's been around a while, and there don't seem to be any significant attacks. So another option, if you want the dual paradigm, where you can get away with this much better stretch in terms of the seed size, then this is more complex to implement, but one option is to use a structured matrix with this quasi-cyclic structure, where essentially multiplying by this matrix corresponds to a polynomial multiplication, so it can be done in quasi-linear time. And this is actually the same assumption that's used in a couple of the candidates that were in the NIST competition for code-based public key encryption schemes. So it's seen a fair bit of analysis in the last few years and some attention from cryptanalysts. But obviously with this, the logarithmic factor overhead makes it more expensive computationally than the primal candidate. And more recently, there was this paper last year from Crypto, which looked at a different approach to instantiating dual LPN, where they defined this matrix H based on the transpose of a generator matrix of a very structured LDPC code. I won't say any more about, since I'm not sure enough about the details myself. But this manages to get the multiplication time to be linear complexity, so improved greatly in terms of computation across the previous approaches. There is some analysis of security in this, but it's this new type of assumption which hasn't seen much study, so it would be nice if some more people looked at this. And then finally, there's another variant I want to mention, which actually isn't relevant for OT and vector OLE, because it's essentially introducing more structure into the matrix and put more possible types of algebraic attacks. But the idea here is that when we want to do OLE or multiplication triples in this silent way, then it's nice to have some multiplicative structure, which we can get by relying on LPN over polynomial rings. This is exactly the same kind of rings used in ring LWE. So this is basically ring LWE with the sparse noise instead of Gaussian noise. So it introduces some attacks you have to be careful of, but if you account for them, then you can still use this efficiently, and it seems to work out well. Again, it's this new assumption from last year or so, so it'd be nice if people took a look at this and studied it further. But this is something you don't need if you just want OT or vector OLE. Okay, so that was the PCG part of the talk. Now I'm going to move on to the setup protocol for actually generating these seeds in the first place. So we can do this without having to rely on a trusted dealer. For this, we of course need to dive into the details of this punctuable PRF. So this is the GGM construction, which can be used to build a punctual PRF, where the sender has this random key k, which is then used to build this binary tree. So at each node of the binary tree is assigned with some key k. We're starting at the root. We expand k using a pseudo-random generator to obtain 2 new keys, and then do this recursively until we end up with n keys at the leaves, where each leaf corresponds to a single output of the pseudo-random function. But having this tree-like structure lends itself very nicely to puncturing. So we want to puncture at this point alpha, corresponding to the leaf node in position alpha. Then we can just give to the receiver all of the nodes which are children of a node on the path from the root towards alpha. So in this case, it's these 3 yellow nodes. We send these over to the receiver. Then the receiver can apply the corresponding evaluation by just obtaining the subtrees for each of its node. Now you see that it then obtains all but one of the evaluations of the PRF, where it's missing exactly the point at alpha for its private index. Okay, so we want to build a setup protocol which will allow us to generate this punctual PRF key in a way that the sender doesn't learn alpha, while the receiver doesn't learn anything about the sender's key, or the missing evaluation. So the way to think about this is in some recursive manner. So let's suppose the receiver's already got these yellow correction values for, say, the first 2 levels of the tree. We want to do this and now get the correction value for the next level. So this is one of these 2 leaves, which are missing here. In this case, we want the one on the right, because the one on the left corresponds to alpha. So to do this, we're going to use an Oblivious Transfer protocol. So the receiver will just input as its choice bit, either left or right, corresponding to which one it wants. And the sender, remember, doesn't know exactly where in the tree we were transmitting these values, but instead what it can do is just take the sum of all of the left children at the bottom of this tree, and then the sum of all the right children. And for the one which the receiver chooses, we know that it will be able to compute all of the other children except for the one it's missing. So it can subtract these and get the right missing value to fill in its tree. And the nice thing about this, when we do use a puncturable PRF, instead of using function secret sharing or a distributed point function, is that if we look at this entire protocol for doing this across the whole tree, then all we're doing is a batch of OTs where at each OT, the receiver inputs a choice bit, which is just based on 1 bit of its input alpha. Meanwhile, the sender is inputting these sums of evaluations of the GGM tree. They can just compute all of these in parallel, and we can do all of these OTs in parallel in a single round of communication. If you compare this with a distributed point function, then the input to the OTs actually kind of change in each level, and you end up having to do things iteratively, obtaining a round complexity that scales with the depth of the tree. So if we plug this in to generate the seeds for the entire setup for silent OT, and for each of these punctual PRF trees, we need log n OTs. They can be done in parallel. So if we have a 2-round OT protocol, we can do this setup in 2 rounds. And that's pretty much everything we need to get the seeds for silent OT. So if T is the noise weight of the sparse error vector E, then essentially the dominant cost is just going to be T times log n of these OTs to set up the trees. One thing is if we're doing vector OLE, then we also need a small kind of seed vector OLE to do some multiplications, which we'll need as well. Interestingly, if we take silent OT and then we want to use this directly to build OT on chosen inputs, where the sender and receiver have their private inputs we want to do OT on, then if we do this in parallel with the setup phase, we actually still get a 2-round protocol. We don't increase the complexity. And that's essentially because in the first round, when the receiver sends its message, the choice bits for the OTs, then it already knows the noise positions for the LPN instance. So it knows the pseudo-random choice bits, which it's going to obtain for its random OTs, so it can already kind of use these to mask its input in the first round. and obtain chosen input OTs directly. So this gives us a 2-round OT extension protocol, which actually compared with the IKNP protocol was not possible previously. So there's actually some kind of black box impossibility result, which says that any OT extension protocol which only uses, say, symmetric primitives in a black box way cannot have 2 rounds. And this is why IKNP has 3 rounds, also related to the fact that it has this transpose step which flips the roles of the sender and receiver you have to account for. So previously, the only approach to 2-round OT extension was an expensive garbled circuit Bates approach, which, relying on LPN here, we managed to avoid. Okay, so lastly, I want to talk a bit about active security. So, just as before in my vector relief presentations, I'm going to follow this in the same kind of spirit by saying, okay, we want to design an active secure protocol. I think the first thing to look at is what can go wrong with an active adversary. So we have this setup protocol where all we're doing is OTs. Let's look at the receiver. If we have a malicious receiver, then Alice is just inputting to each OT one of these choice bits corresponding to 1 bit of this position alpha, which is an LPN noise coordinate. So if she inputs a different bit here, it's just changing the value of alpha, and that's basically only there to help her security. So by doing something different here, she's not actually breaking the protocol in any way. So the tricky part, as usual, is when we have the sender who is supposed to input these 2 messages, which are the sum of the leaves of the GGM tree. So if the sender just inputs one of these incorrectly, then it can completely break the privacy of the protocol. You can end up with some garbage outputs of the PRF tree, which translate to incorrect OT outputs. So the natural thing to try to address this is to perform some kind of verification stage where we can actually check the consistency of this GGM tree after we've created it. But we're still going to have the problem here that because we're using OT, then we allow selective failure attacks. So, if the sender inputs a message just into the sum of the left input for the OT, then this will only cause an error if Alice's choice bit was left. So this kind of translates into the corrupt sender being allowed to try to guess a few bits of the secret LPN noise coordinates known to the receiver. And of course, it will only succeed if all of these guesses it tries to make actually succeed, and otherwise the protocol will abort. We can actually model this kind of leakage as a kind of variant on LPN where we have we allow the adversary to make a very limited type of guess on the noise coordinates of the instance, which essentially translates into, on average, 1 bit of leakage on the noise coordinates. So in practice, that makes no difference, and you can always slightly increase the entropy or the parameters if you want to compensate for it. Okay, so how can we check this consistency? Well, so let's go back to the leaves of the GGM tree. So on the right, the sender has all of the leaves. On the left, the receiver has the punctured key, so it has all but 1. And to check correctness, we're actually going to go a step further and expand this tree to have twice as many leaves. So by just applying another layer of POG evaluations, imagine this is now a tree which has depth 1 more, so twice as many leaves. And on this new layer of leaves, the receiver will have all of the outputs, so it's still just missing 1 overall. So now we're going to have the sender compute some check value to verify consistency of the tree by just taking a hash function and hashing together these new leaves we created. And now the receiver knows all of this second layer, so it can just receive the hash value and check that this gives the right thing. And it turns out that if this check passes, then we're actually guaranteed with high probability that the original tree was chosen in a consistent way. Of course, the catch here is that at this point we have to account for some leakage of the position alpha known to the receiver, because if the sender did cheat, then it might have just guessed the right amount of information to be able to come up with the right hash value, even though things didn't go quite as they were supposed to. But if you do that, then you can make this work out and prove that you can get a consistent tree. But this isn't quite enough for the entire silent OT protocol because of one detail which I kind of missed in the explanation before, which is that for each of these trees, we actually want to use this to multiply the sparse vector by this value delta. And we can incorporate this on the last level of the OTs we do by just having the sender send some extra value to correct things. But the problem is they might use different deltas in different tree instances. And since the hash check is just checking a single tree at a time and it's independent of delta, this doesn't catch this issue. So solution here is, of course, another consistency check, where we now take a random linear combination sampled by the receiver across all of the punctual PRF trees. And this is kind of seen as like a MAC check on the correlated OTs. It's also used in MPC protocols and zero-knowledge protocols. So it's a standard kind of technique. And if you have the hash-based consistency check as well, then this turns out to be enough to prove security of the overall protocol, ensuring things are consistent. So this was an approach that we took in the paper from CCS 2019. So since then, there's been a couple of follow-up works which have simplified these checks slightly. So in the Ferret and Wolverine papers, which do correlated OT and vector OLE respectively, they don't do the hash check on the trees. They actually do a linear combination on each tree separately instead. And the way they take the linear combination there actually means that they can also account for the deltas amongst the different trees and ensure that these things are consistent. So this check is a bit simpler. You don't need a hash function, so it's cheaper in terms of computation. And you also don't need to expand these trees to an extra layer at the end. But again, it has the same kind of issue where, of course, the sender can always try to cheat and guess a few coordinates of the LPN error vector. Okay, so what about performance? So here's a table of most of the relevant protocols. Firstly, the IKNP style protocols. Actually, this is like the most kind of optimized state-of-the-art IKNP style OT extension, all with active security. And to generate 10 million random OTs, with IKNP, you need this huge amount of communication, around 160 megabytes. You can do this in under half a second. It's pretty cheap. Whereas if we switch to silent OT extension, then the very first implementation we did, where we used the dual LPN instance instantiated with quasi-cyclic codes, drastically reduced the communication by more than 1,000 times. The cost of some increase in computation up to around 5 seconds or so. So this is a huge difference. This is kind of the most extreme trade-off. There are different parameter settings where you can reduce computation a little and increase communication. But if you use some of the different instances of LPN, then you can actually reduce the runtime much further. So the Ferret paper took the primal approach, which in theory doesn't have such a great stretch, so should have much worse communication, but actually with some nice optimizations and this kind of bootstrapping style approach where they use some of the output correlated OTs to reduce the cost of the setup for a next instance of the silent OT, then you can reduce communication pretty good and still get it to around half a megabyte after some extra one-time setup cost, and reduce the runtimes by around a factor of 10. Whereas the Silver approach from last year, which took this structured LDBC instantiation of the dual code, then retains the same small communication as the previous dual approach, but reduces the runtimes further down to just 300 milliseconds, which is actually even faster than the IKNP style OT extension. And that's kind of amazing that we can have this silent feature and get something computationally, at least in this specific case of a single core of a CPU, faster than IKNP. And I think the main reason this is possible actually is if you go back to the basic structure of these protocols, in IKNP, we have this transpose step. And computing a matrix transpose is actually not such a cheap operation. It's not very cache friendly. It has to be done very carefully. And by doing these silent OT approaches, we don't do matrix transpose. And that's what allows you to shave off this extra few milliseconds if you have a fast enough encoding with the dual approach. Okay, so that's about all I wanted to talk about for these protocols. So let's sum up quickly. So I mostly talk about silent OT, but everything I said can be extended to build vector OLE with only fairly small changes. And the main idea which I want to get across today is that by exploiting this somewhat linear structure of LPN with these noise terms, then we can expand things locally to get silent protocols by taking compressed sharings of sparse vectors and expanding them to longer pseudo-random outputs. And the key tool here is this punctual PRF, which is kind of a simpler form of function secret sharing. And then we have these setup protocols, which are very simple, only 2 rounds, can be made actively secure with lightweight consistency checks, and even be used to get a 2-round OT extension protocol on chosen inputs. So even though these protocols are really fast, I think there's still some open problems which could be interesting to address. So one thing I haven't talked about, but has been mentioned a few times at other talks in the school, is many different applications of PCGs and silent OT. So I think it's interesting to look at applications which can really take advantage more of these features. So it's such a massive change compared with regular IKNP extension to silent OT in terms of the efficiency characteristics. Maybe there are certain things, if we design in the right way, then we can exploit this and make the best use of it possible. Another really interesting open question is to build this punchable pseudo-random function in a more efficient way. So, of course, we want to do this t times for each error point, each non-zero position in the error vector. And the naive way to do this involves this t-factor repetition. Well, you can get around this using structure regular errors. It's nice to avoid that assumption. This is also related to the question which Alette asked at the end of her talk about doing the same thing for distributed point functions. But of course, punctual PRFs are a simpler object. So I think it's definitely easier to look at this case instead and see if there's something possible. Go to the setup protocol. So we have these 2-round protocols where the structure is Alice sends a message and then Bob sends a message, depending on Alice's message. But for building random OT, it might actually be feasible to do something in just 1 round. So that would be the dream if we can do the setup phase where Alice and Bob both send a parallel message. And I don't know how to do this with the LPN-based constructions, but it would be really nice to achieve while still getting the fast computation and efficiency benefits of silent OT. And then finally, I think a really big question, especially as these things are becoming so much faster and much more practical, is to closely investigate the security of these different variants of LPN. So while the primal version and the quasi-cyclic version, I think, are fairly well studied, and may be reasonable to use in applications now, I think the more recent ones, like the structured LDPC used in Silva, and ring LPN used in other applications, as well as variable density LPN, which Yuval talked about yesterday, they all seem plausible from the analysis that have been done, but in terms of the exact concrete security you get, I think there's a lot that still needs to be understood and work that can be done. Okay, so that's about all I wanted to cover. I guess we have plenty of time for questions.
Okay, so we have one question. Mm-hmm. So the question is, where else are punchable PRFs used?
So where is it used?
Mm-hmm.
Where else or where in this protocol?
Where else?
Where else? Oh, okay. That's a good question. So they were actually first introduced back in 2013-ish in the context of indistinguishability obfuscation. So it's kind of very different application, but it turns out they were really useful theoretical tool for making constructions work in a provable, secure way by using punctual PRFs inside obfuscated programs to generate values pseudo-randomly. And that was like the really big one. One other much more practical application I can think of is, I think, forward security in TLS. So there've been a bunch of papers recently on the last few years on forward secure key exchange, where they use puncturable encryption, which I think in some cases can be implemented with a punctual PRF.
Okay, thank you.
All right.
Okay.
Thank you very much, Peter, for a great talk. We will resume after the lunch break for your second talk.
Great. Thanks, everyone.
Oh, hi everyone, and welcome to the afternoon session. And the first speaker is going to be Peter Scholl in his final lecture in this school on pseudo-random correlation functions from BIU. And Peter, the stage is yours.
Thanks, Benny. So yeah, this is the last part of this series of talks on PCGs. And the topic here is going to be a little bit different. So there is nothing to do with LPN here, which may be refreshing if you're sick of that. Instead, we'll look at constructing PCGs and more generally PCFs from number theoretic assumptions like BIU and factoring-based assumptions. This is a recent work based on a paper from Eurocrypt last year with Claudio Orlandi and Sofia Yakubov. Okay, so I'm going to start by recapping what a PCF is, a pseudo-random correlation function, the definition there. And then I'll present our results similar to the last talk in terms of some kind of general blueprint for how you can construct this kind of object, this time based on the right kind of encryption scheme with some special properties. And then I'll show how we can instantiate this based on different kind of schemes to give PCFs for different correlations like vector OLE and OT. And then finally, I'll talk about a non-interactive setup protocol for these PCFs, which is based on similar kinds of techniques and allows us to get this special public key setup property to give like almost the minimal level of interactions possible in a protocol like this. Okay, so you've seen this slide a million times before, so I'll skip this, but that's just the motivation. So what we're interested in constructing is a pseudo-random correlation function, which will allow us to generate all of this preprocessing material for MPC. More formally, so we have this key generation algorithm, just like the case of PCG, which outputs a pair of correlated keys to the two parties. And now, instead of having a single expansion step, we want to be able to evaluate this PCF in a kind of random access-like manner, somewhat analogously to a PRF compared with a PRG. So the evaluation function takes as input a public nonce, which is known to both parties, as well as the private key, and then outputs this piece of correlated randomness. So R0, R1 is supposed to be indistinguishable from a fresh sample of the desired correlation. And then for the security property, we again have this notion of security against insiders, where even if one party knows one of the keys, then the output of the correlation should be, in some sense, pseudo-random still, or indistinguishable from a fresh sample. Okay, so what's known about how we can actually build PCFs? Well, there's a few different constructions previously. So that's the most general one is if we use LWE and building on top of special flavors of FAG, which I'll talk about shortly, we can build PCFs for any additively secret shared correlation. So this is just a correlation where you apply some arbitrary function on random inputs and then secret share the results each time you want to evaluate. This is a not very efficient construction. It requires LWE and homomorphic evaluation of a very complex function and even some bootstrapping steps for multiple parties. But you can do it with just a CRS setup and a public key from each of the parties to generate the keys. So it's a nice feasibility result. If we want something more concretely efficient, there's this variable density variant of LPN, which Yuval talked about yesterday, which we can use to get very simple low degree correlations, including OT, volley, even constant degree polynomials. But here we have to pay a bit more in the setup. We have this more expensive trusted setup phase, which generates DPF keys, which you can also replace with an interactive protocol, but it will be several rounds. And then in this talk, the ones I'm going to focus on are instead based on public key type assumptions like quadratic residuosity and the decisional composite residuosity assumption used in BIU. These constructions can produce correlations for OT or volley. And just like the LWE case here, we require only a CRS and some public keys broadcast by the parties. So it's this kind of minimal setup. Okay, so as a warm-up, I want to go through this FHE construction based on LWE at a very high level. So we can build a general PCF from this type of object and then look at how to optimize that construction to get something more efficient. So suppose we have an FHE scheme. In the key generation algorithm for the PCF, we just sample a public key and give out some encryptions of a random seed S, which is going to be used for a PRF. And then in the evaluation phase, the parties have this public nonce as input, which they use to define a program which is going to be evaluated on the FHE ciphertext. So they each locally perform this evaluation, obtain some encryption of an output, and then we rely on a special property of the FHE scheme, which is that the parties can actually take the ciphertext together with some private key material from the setup, and then non-interactively obtain a share of the result. So they get these shares Y0, Y1, where for correctness, we require that they sum to the right thing. So for instance, if we want to produce a PCF for beaver trebles, they produce a beaver treble. And in that case, the program P, which is evaluated homomorphically, will be defined to use the PRF S to generate pseudo-random values A and B, and then multiply A times B. And obviously, evaluating this PRF inside FHE, so every time you want to do an evaluation, is very expensive and something we want to avoid. But taking this basic blueprint, is there some way of optimizing this? So notice that for the beaver treble case, most of the work is just generating these ciphertexts which encrypt random values A and B. So if we can somehow avoid that, then we just need to do one multiplication and maybe things become a lot cheaper. So for instance, if we had a way of obliviously sampling ciphertexts, so we can somehow agree upon using some public randomness, a random ciphertext to which no one knows the underlying message, then we can do this. Unfortunately, this seems to be a kind of hard problem with LWE, at least. So there are some candidates that have been used in recent constructions of obfuscation based on LWE-like assumptions. But unfortunately, they're super expensive and they require non-standard assumptions. So it's not something we want to go for at the moment. However, this is, of course, a very interesting open problem. And if you can achieve this efficiently, then as well as building I/O from a standard assumption, you would get efficient PCFs. So this is a super nice problem to try and tackle. But in this talk, we'll go for something different and look at different kinds of encryption schemes, which might be easier to do this with. So for instance, the Pellier and Goldwasser-Micali encryption scheme both have a dense ciphertext space, where if you just sample a random element from the ciphertext space, then with overwhelming probability, it should be a valid ciphertext. And the problem, of course, is that these schemes are not fully homomorphic. We only have this additive homomorphic property, which then isn't enough to multiply A and B if we want beaver triples. But we can instead do something a little different, which gets us something close. So this time, our blueprint for building a PCF is going to be the key generation algorithm, where we'll give out some kind of correlated PCF keys, where in particular, one party will get the secret key of the encryption scheme, and another party will get some random value X, which is used as part of a PCF correlation. Then we have the PCF evaluation stage, where instead of doing homomorphic evaluation of encrypted ciphertext, we'll use our nonce and then perhaps feed it through a random oracle to just obliviously sample this pseudo-random ciphertext. So it's an encryption of a random message R, which now only the party with the secret key can decrypt. And obviously we can't multiply ciphertext, so instead what we're going to rely on is a special kind of shared decryption procedure, which can additionally do one multiplication with this value X, which was distributed to Alice at the start. So you can combine the shared decryption to decrypt shares of R with a single multiplication by some fixed scalar, and then you get these Y0 and Y1, which are shares of R times X. If you see repeating this evaluation procedure many times, each time we get a fresh random ciphertext R multiplied by the same X. So this is exactly a very long instance of vector OLE. So we're going to instantiate this using Pellier encryption to start with. So I'll start with a bit of a background on that. So PA works with an RSA modulus n, product of two primes. And then instead of working in the integers modulo n, we'll actually work in the larger group, mod n squared, seen as a group under multiplication. And this group has a special element 1 plus n, which we'll call G, which is special because it generates a subgroup of order n, where the discrete logarithm problem is easy. So to see this, note that if we take 1 plus n and raise it to the power of any x, then if you apply binomial expansion, it's quite easy to see that this just gives you this linear relation, or linear function 1 plus n times x mod n squared. So that means that we can take the discrete log of any element y to the base of 1 plus n by just subtracting 1 and dividing by n over the integers. So this allows us to solve discrete log with respect to this special base, which gives us the special properties useful for Paley encryption. Another useful fact is that this whole group is actually isomorphic to a product of the integers Zn under addition and Zn under multiplication. And this isomorphism actually exactly defines the encryption algorithm, which takes the plaintext x and some randomness r and encodes this by taking the special base g to the power x times the randomness raised to the power n. And to decrypt the ciphertext, okay, so first, yes, so this encryption algorithm implies oblivious sampling exactly because we have this isomorphism. So any ciphertext that is a part of this ciphertext space can be decomposed into this form and viewed as an encryption of a valid message under some randomness. And finally, in PA, the decryption algorithm can be written in this form, where the secret key is just a special integer defined by the factorization of n, such that if we take a ciphertext, raise it to the power d, then we get g to the x. And now we can just solve discrete log to recover x. Okay, so that's everything we need to know about PA. And with this, let's take a closer look into this shared decryption algorithm. So we'll start with a simpler case where we just want shared decryption without multiplication. So the parties both have this ciphertext encrypting a random value r, and then they have additively shared this special secret key d, or in this case, subtractively shared over the integers. And the goal of shared dec is to output shares of the encrypted value r. So parties will start by applying decryption on their shared secret key. So take the ciphertext, raise it to the power d0 or d1. Since c to the d gives us g to the r, then now the ratio of these two group elements, g0, d1, will be g to the power r. There should be an exponentiation there on the slide. So this is kind of some kind of nice relation, but it's not quite the additive relation we want on the final output shares. So the final goal is to run a distributed discrete log procedure where the parties can non-interactively convert this divisive sharing of g to the power r into an additive sharing of the value r, which will be shared modulo n. Okay, and then building on that, if we can do shared decryption, what we additionally want to do, remember, is actually shared multiplication, where we additionally multiply by the scalar x whilst we're decrypting. Oh, sorry, scalar y now. So in this case, as a setup, instead of shares of the secret key, we require shares of the secret key times by y. And now the parties just run exactly the same thing, raise the ciphertext to the power of their share, and this time instead of g to the r, we get g to the r times y when we take the ratio of the two group elements. Now again, if we have a distributed discrete log procedure, we can just convert these group elements into additive shares modulo n of r times y. Okay, so if we can do that, then we can plug this into the PCF blueprint and get a PCF for vector OLE. So the only missing piece is this distributed discrete log algorithm. So this problem of finding a distributed discrete log goes back to the DDH setting, where it was studied for homomorphic secret sharing in 2016. So I'll recap the challenges of the DDH setting before going into how we do this over Pellier to make this work more efficiently. So suppose Alice and Bob have this divisive sharing of group elements G0, G1, which is G to the XY, where here now G is just going to be a generator of the entire group, not this special element in Pellier. Okay, so we'll look at these group elements on a circle where we kind of separate each item by multiplying by powers of G, which represents the entire group generated by G. And now if Alice and Bob can somehow measure the distance in terms of powers of G between their two group elements, and then they can get X and Y. So we want to do this in shared form. And one candidate approach for doing this is agreeing on some fixed element in the group, say some element H, and then measuring the distance from G0 and G1 respectively to H. So if we do this by just counting the number of multiplications by G in each case, we get an integer, which should then be an additive, or in this case, I think subtractive share of the integers of the correct value X times Y. Okay, but there's a couple of problems here. So firstly, if either of these shares are large, then you're just counting this number of multiplications until we get to H is going to be prohibitively expensive. So it's going to be exponential time in the worst case. So one workaround for this is to have several distinguished elements. So we can have some pseudo-random way of determining whether a particular group element is distinguished or not, and then choose the density of these appropriately so that we have enough of them. Another problem we have, of course, is that this restricts us to a polynomial-sized message space. Because it's kind of inherent that these two share sizes, XY0 and XY1, will have to be at least the size of the message. And again, if we have very large messages, we're going to get into this extremely inefficient range we want to avoid. So that's a kind of inherent limitation. But then finally, there's another really annoying problem, which is that once we have many of these distinguished elements H, of course, they might not end up finding the same H. So if there's another element in between Alice and Bob's initial group elements, then we'll get inconsistent shares when they try to measure this distance. So with probability inverse polynomial in the security parameter, we end up having this probability that they get the wrong thing. So even with this inverse polynomial error probability, this algorithm is useful for certain things. It gets you this homomorphic secret sharing scheme, which has many interesting applications for MPC. So there's been a lot of effort to improve this and give various optimizations for reducing the error. But despite all this, it's still computationally quite heavy. And there's always this inverse polynomial probability of correctness error and the limitation to small message spaces. So there was also another variant used in Pellier groups, which actually had the same limitations as above and didn't manage to overcome them. So of course, the question is, can we somehow do better by exploiting the special structure of the Pellier groups? And interestingly, there was this work from Crypto 2018, which studied this discrete log or distributed discrete log problem in a more general framework and showed that solving this reduces to solving some variant of the discrete logarithm problem. So it's unlikely to be able to improve upon this correctness error from previous works. However, if you look at this reduction and apply it to the Pellier setting, then it simply translates to solving discrete log in the subgroup where Pellier is easy. So if we now plug this into the Pellier setting and work in this special subgroup, so where we replace this element G with the special element 1 plus n. Now 1 plus n doesn't generate the whole group. So instead, when we look at this circle, we're actually looking at a coset of elements in the group defined by, say, G1, Alice's element, and then multiplying by powers of 1 plus n. Okay, but we can try to do the same type of approach. So if we use just a single distinguished element here, which is what we want to aim for if we try to reduce the correctness error in the previous approach, then the parties can measure their distance to this element by just taking their input group element dividing h by the input, and then this gets us some power of 1 plus n to their share, and then they can apply the discrete log algorithm with this base to recover the share. And this is essentially all works just because the discrete log algorithm is easy in this group. However, the only challenge is that they have to agree upon this element h, right? Because we're not in the whole group anymore. We can't just pick a random group element. We have to find one that lies in the same coset defined by the element g1. It turns out if they both just define h by taking g1 modulo n or g0 modulo n, firstly, this gives the same value, which is quite easy to see from the fact that g0 over g1 is 1 plus n to the xy. And secondly, this gives us something which lands in the right coset. And as long as that's true, then we can always apply this discrete log algorithm, and we get something which ends up working with an exponentially large message space and a negligible probability of error for this share conversion procedure. Okay, so I'll just go through this in a little bit more detail and show why this works. So we have these two inputs, group elements G0 and G1, where after the first part of this shared decryption protocol, we know that G1 is equal to G0 times 1 plus n to some power z. And the goal is to agree on this element h, which is in the same coset as G0 or G1. Where I said if we define h to be just G0 mod n, which equals G1 mod n, then this will be the case. Okay, so why is this true? I'll just switch to my pen here to go through this proof. So we want to find such an h. So let's first suppose that we have an h. So suppose h is equal to G0 times 1 plus n to the power I for some I. Okay. So then we can rewrite this slightly by taking G0, representing it as h plus some h prime times n. So remember, h is G0 mod n. And then on this right-hand side, we have this nice fact from Payet that we can write this as 1 plus I times n mod n squared. Okay, so now multiplying this out, we get h equals h plus h prime plus I times h n, and then reduce mod n squared, the rest goes away. And now remember, we want to solve this to find I. So first we can see that these h's cancel out, and then we get I h n is minus h prime n. This is mod n squared, so if we divide by n, then we end up with a relation modulo n. So we actually get I is equal to minus h prime h inverse mod n. So if we can compute this, so as long as h has an inverse mod n, which it always should do if we start with this, then we can compute this I such that h lies in this coset. And we are done with distributed discrete log. Okay, so so go back to the PCF for vector only a second. So we've seen how it works, and before moving on, I want to give a slightly different perspective on this. By viewing this in the same way that Yuval presented this PCF from variable density LPN yesterday, in the lens of a weak pseudo-random function. So we have this procedure where we're taking a random ciphertext C, and we're essentially decrypting it to get a random message. And if we look at this as a function depending on the decryption key with input this random ciphertext, then this is actually a weak pseudo-random function, where we call that a weak PRF as one that is secure as long as the input, in this case C, is a random value. So we take a random ciphertext, and assuming pay is secure, this gives us a random message. So now when we're giving out these additive shares of d times y, so we can do this distributed multiplication and decryption to shares, then this is kind of equivalent to giving out FSS keys for a function class, which is scalar multiples given by y times the evaluation of the weak PRF. So this is how you can see this as an instance of this framework, which I think isn't so helpful for coming up with the construction, but is interesting to compare it with the other types of constructions we know. Okay, so another variant we can do with the same kind of construction is getting a PCF for Oblivious Transfer. And here, well, it's essentially take the same thing, but instead of PIA, we'll plug in a different encryption scheme, which is going to be Goldwasser-Mercalli. And recall that for OT, it's enough if we can just build correlated OTs, which is this batch of OTs where the receiver's messages are of the form yi equal to ri, the secret choice bit, multiplied by this fixed delta known to the sender, plus some other random string y1 known to the sender. If we can get correlated OTs, then we can always hash these to get random OTs, and that's enough. Okay, so in the Goldwasser-Mercalli encryption scheme, unlike PIA, which encrypts integers mod n, here we're just encrypting a single bit. And this bit is going to translate it into the choice bit in the OT. And ciphertexts now are just elements of the integers mod n instead of n squared. And we can define this secret key very similar to the PIA case, where if we take a ciphertext C and raise it to the power of the secret key, and we get this special element -1 raised to the power b. So now this is either 0 or -1, depending on the bit. And you can kind of view this as mapping into a subgroup of size 2, where the discrete logarithm problem is easy, analogously to PIA, which maps it into this subgroup of size n, where the discrete log is easy. Okay, so given this encryption scheme, we want to construct now a distributed discrete log algorithm. But now, because we have a plaintext space which is only a size 2, this is actually really easy. We can basically just do the trivial brute force method. So on input is ciphertext, let's call it y. We just want to map it into 2 distinct cases, which will be consistent with what the other party does. So we're going to say if y is less than n over 2, we output 1, otherwise we output 0. So now if we give them 2 y's, which have this ratio of -1 to the b, which we'll get if we try to decrypt with shares of the secret key, then we take the dd log and XOR these together, we actually end up with the right bit b. That's because if one of the things is less than n over 2, then when we flip the sign, we end up in the opposite case. So you can see this as equivalent to XOR. Okay, so given this, the PCF is pretty simple. The only catch compared with the PIA case is we now have to repeat this bit by bit to be able to build up correlated OTs, which are of the length we require. So if we want them to be like the security parameter, as is common, then we have to do this security parameter times, giving out shares of the secret key times each bit. And then we sample an oblivious ciphertext, which will be the receiver's choice bit, and then run this shared decryption procedure to get some shares of Ri times delta. So the main cost of this is just repeating this lambda times, where we have to do 1 exponentiation modulo n for each of these bits. Okay, so for a quick summary of the PCFs, the ones we've seen from number theoretic assumptions build these 2 correlations, either volley in Zn or correlated OT, or equivalently random OT if you use a hash function. And first off, for the key generation phase, we require this special setup, which for the PIA case is just additive secret shares of the integers of a secret key times by this fixed scalar x. Whereas in the QR case, we just need to repeat this lambda times each bit delta I. And then the cost per eval is just 1 exponentiation for each of these elements, which to generate OT actually ends up being quite a lot. We have 128 exponentiations. For both of these, the key size is actually really small. And even when you have 128 of these, we still get a key of only around 50 kilobytes for QR or 1 kilobyte for Pallier, which is way, way smaller than even the PCG constructions from LPN. So one natural question is to wonder, okay, can we take this PCF for vector OLE and then use it to somehow build a PCF for OLE, where we can get independent multiplications instead of always multiplying by the same x. And if you look at the setup phase of the Pallier construction, you might think like, okay, this is kind of an OLE. So what if we instead have a bunch of different setups with the same D and different x's? Then this is like a vector OLE. So maybe we can do some kind of bootstrapping and extend this. One problem here is that the setup shares have to be of the integers for decryption to work. Because when we do exponentiation, we work modulo the order of the group. So you can't directly bootstrap using the same PCF because the PCF gives outputs modulo n. However, what we can do is build a separate PCG or PCF from an LPN style assumption where we tweak the PCG slightly so that it outputs something that can be viewed as shares over the integers. And we use this to generate the setup for the Pallier construction, and then kind of bootstrap from there to repeat the Pallier construction a batch of times and get OLEs, or even PCF for arbitrary decree 2 correlations by combining these two things. So here the setup cost is roughly proportional to the setup cost of the PCG for vector OLE, and then the computational cost for evaluation is going to be similar to the PCF for vector OLE from Pallier, where we have 1 exponentiation per output. But now we have the extra key size coming from the LPN-based construction, as well as the extra assumption. So it's kind of a hybrid of both worlds. It inherits both the best and the worst parts of each of them. And finally, we can also compare these with the VDLPN-based construction. So looking back to that one, the main disadvantages of VDLPN are that we have this more costly setup phase. We use many distributed point functions. It's not constant round to generate these keys using a secure protocol. And again, the key sizes are quite large. Depending on the flavor of assumption you use, whether it's a conservative or less so, the key size ranges from 100 kilobytes or so up to a couple of megabytes. And of course, these assumptions are somewhat new and untested, and I'd like to see more research in this area. Of course, the big benefit of using LPN is that we avoid all these expensive exponentiations in RSA groups, and we have much faster computation. So as a rough estimate, with the most aggressive choice of parameters for VDLPN, we can do about 20,000 evaluations a second on 1 core of a modern CPU. Whereas doing Pallier exponentiations, these are super slow, modulo n squared. You can only do about 100 evaluations a second of your vector OLE. And with OT, this gets even worse because you have to repeat this 128 times. So there's maybe a couple of evaluations a second. So these number theoretic ones, they're super simple. They have really small keys. They're very implementable. So if you don't mind these slow evaluation times, it's fine, but it's not so scalable. So VDLPN still seems like a competitive candidate from that respect. Okay, so maybe I'll pause and see if there's any questions from there.
No, absolutely no questions so far.
Okay, great. And how are we doing for time? I guess okay. So I'll just mention as a quick aside that these techniques we've shown for Pallier can also be used to construct homomorphic secret sharing. So homomorphic secret sharing is kind of the jewel of function secret sharing, which Alec talked about on Sunday. We want to be able to secret share inputs and then locally evaluate some program on the inputs to obtain shares of the outputs. By applying this shared decryption technique, we can get HSS for a class of special restricted multiplication circuits, where each multiplication gate in the circuit has to be between an input wire and an intermediate value in the computation. It turns out this class of circuits is roughly equivalent to log depth circuits or branching programs. The idea of the construction is very simple, and we just give out encryptions of the inputs to the program, and as well as secret shares of the secret key. And then for each multiplication, we use this shared encryption algorithm to combine and pair together these encryptions with the secret shared intermediate values and do one multiplication. And this constraint on the multiplication gates exactly fits the constraint on the multiplication algorithm we have from Pellier already. So of course, compared with previous HSS constructions like DDH, we have exactly the same advantages of the share conversion algorithm, where we can get this negligible correctness error and exponentially large plaintexts, which weren't possible with previous constructions. And you can also compare this with lattice-based constructions of building HSS, which are a bit more efficient in terms of computation, because if you use ring LWE, the computational costs are much faster than Pellier. But on the other hand, Pellier ciphertexts are smaller than ring LWE ciphertexts, so there's some trade-off there. Okay, so that's enough on HSS. The last thing I want to talk about today is concerning the setup phase of the PCFs. So remember, in both of the cases, we essentially have the setup, which is just additive secret shares of a single product or a set of products, where one party has a secret key D, and then the other party either has a scalar X or bits delta I. Now, both of these things are just instances of OLE, right? So we can have a setup protocol where the parties just run one OLE, generate these shares, and then they're done. Okay, but what's the minimal level of interaction we can do this setup with? So a standard OLE protocol, at least the ones I talked about on Sunday, these are two messages. So we have a message from the receiver and a message from the sender. But in this sharing kind of setting where we're just generating shares of a single product, can we do this with a single parallel message? And this type of setup would give us then this public key flavor of setup where Alice and Bob can independently generate a public key, broadcast this once and for all, then use their private key to derive the PCF keys. And it turns out by exploiting the same kinds of share conversion techniques which we use to build the PCFs, we can also build this public key setup in a single round. Okay, so I'm going to describe this construction quickly. Again, switch to the pen. So let's say Alice and Bob each have X and Y. The goal is to obtain shares of X times Y. Practice, we want it over the integers. Here we're actually going to do it modulo n for some RSA modulus. If you want it over the integers, then you can just choose this n here to be much, much bigger than the bound on the integers you want. So you choose it to be a different RSA modulus than the one you actually use in the PCF, and then you can view the shares over the integers, essentially. But anyway, in the construction, we'll have a CRS, which is going to be this RSA modulus n, which is p times q, where nobody knows the factorization. So this is a foremost trusted setup, but just a one-time setup. And then we additionally have two random group elements, let's say G bar, because we've already used G, and an element C, which are both sampled from Zn squared. Okay, now given this CRS, we want Alice and Bob to each send a single message and obtain shares of X times Y. So the idea basically follows a classic OT protocol from the 90s by Bellari and Bacali, which itself is very similar to Diffie-Hellman key exchange. So let's just start by looking at Diffie-Hellman. So suppose Alice sends G to the R. Let's call this some group element A. And Bob sends G to the S. Let's call that B. And okay, we want to actually incorporate the inputs in the message. So we're going to have Alice multiply her G to the R by C raised to the power X. Now, this isn't the full protocol, but let's just look at what happens here if we follow in the spirit of a Diffie-Hellman key exchange. So Alice can define a key. Let's call it K0, which is Bob's message raised to Alice's secret R. Okay, so this is, of course, G to the RS. And similarly, Bob can define a key, K1, by taking A to the power S. And this is now going to be, okay, G to the RS, but we have this extra term from C to the X. So we get C to the XS. Okay, now if we look at the ratio of these two keys, K0 and K1, what we have is this C to the XS term. Remember, if we want to apply distributed discrete log, then we want Alice and Bob to get two group elements where the ratio is actually going to be, say, some 1 plus n to the xy, so that they can decrypt it locally and get shares of xy. So if we can somehow switch this C to the XS to be 1 plus n to the xy with a bit of correction value, then we can make this work. And we'll do this by having Bob send one more value. Let's call this D. And this is going to be C to the S, so his secret S, now multiplied by 1 plus n to the power y. Okay, and we do the same computation as before. So now Alice ends up with something slightly different. She has B to the R, which is, and she takes this and, yeah, okay, she will now multiply this by D to the power X to incorporate both of the inputs into this key. So this gets us G to the RS, now times by C to the SX, and finally 1 plus n to the x times y. And now if we look at the ratio of these two things, well, the C to the XS cancels out. We have this on both sides. And the only thing that's left is this 1 plus n to the power xy. So if we feed these two shares into the DD log procedure, then what we end up is additive shares modulo n of x times y. Okay, so that gives us something correct, exploiting DD log. A quick note about security. So if we look at the messages that Bob sends, so we got this kind of G to the S value, and then C to the S times by 1 plus n to the message. So G and C are these random CRS elements. You can kind of view these as an Elgamal public key, and this is now like an Elgamal-like encryption in the Pellier group. Now, because G and C are CRS, no one knows the corresponding key, so no one knows the discrete log of C to base G. So this hides Bob's message Y. On the other hand, for security, when Bob is corrupt, if we look at Alice's message, well, we have G to the R. This was a random group element, and we can show that under the Pellier assumption, this hides the X when multiplied by C to the X. So this gives us a passively secure protocol where we have a single round to, with minimal interaction, generate the shares of X times Y. Okay, so just to recap this whole public key PCF, I'm just going to give a quick summary of the protocol flow when you put all of this together. So we have the CRS setup, which gives out this modulus, which the parties then use for their OLE message to set up the keys. So using DD log, they can obtain the right shares and get their PCF keys, which each party then feeds into the eval algorithm, given some public input I. And then they can use this to generate as many OTs as they want, or vector OLEs as they want, completely silently. And this is the public key PCF kind of protocol flow for any PCF with this nice non-interactive setup property. Okay, so to conclude, we've seen PCFs and pretty general blueprint for constructing these things, starting from the general expensive construction from multi-key FHE, and then trying to optimize this via Oblivious ciphertext sampling, and an encryption scheme that supports this special decryption into shares. We can instantiate this with Pellier and Goldwasser-Micali to obtain very simple, reasonably efficient, I would say, schemes. Not great, but certainly usable in some scenarios, I would say. And we get these PCFs with a very cheap setup, but somewhat expensive computation. We also have this non-silent OLE protocol from Pellier, which is used to generate the setup procedure with this simple one-round protocol to get the public key setup. So there's a bunch of open problems in this kind of area, which I think are interesting. So first off, I think it'd be really nice to take this general blueprint of building PCFs and see what other encryption schemes can be used to be plugged in there. So Pellier and Goldwasser-Micali are just the first ones we found. There might be others which work naturally, or maybe we can design new schemes which have this right ciphertext structure so you can sample obliviously. The advantage of doing this is we might be able to obtain PCFs for different correlations. If we can do this with a, say, a different kind of homomorphic encryption scheme or a functional encryption scheme may be interesting, as well as building PCFs from different assumptions. On a related note, I think it would be really nice to have something to generate OT, avoiding this security parameter blowup when we plug in Goldwasser-Micali. So one potential way to do this would be have something where we don't have to work one bit at a time. So for instance, in Pellier, if we could obliviously sample a ciphertext, which we know encrypts a single bit, then we could actually already do OT immediately, because then we could view that as a vector OLE, where the receiver's inputs are always 0 or 1, and then see this as a correlated OT and hash to get random OT. Unfortunately, this seems like a really hard problem with Pellier, but maybe there are other encryption schemes where you can actually make this work. And thirdly, for the public key part of the PCFs, we, of course, rely on this CRS, which is the trusted RSA modulus. So having something without that setup would be nice to have. And then finally, this is something I also mentioned in the previous talk, is that for the LPN-based PCGs or PCFs, we currently have at least a 2-round setup to generate the punctual PRF keys. And it'd be really nice if we can replace this with this nice public key flavor setup with just a single parallel message from each party. And finally, one big tricky question, I think, for a lot of these kind of constructions is going beyond 2 parties. So this chair conversion procedure and distributed discrete log, if you try to apply this with 3 parties, it doesn't seem to work. Also similarly for LPN-based constructions, even if we move to distributed point functions in the 3-party setting, and then these are much, much less efficient than the 2-party ones, which introduce challenges when you want to build certain kinds of PCGs or PCFs in these settings. So that's everything I wanted to cover. So happily take any more questions.
Unfortunately, there are no questions in the Slack, but maybe I can ask one. So
Sure.
if you go back to the big picture from the beginning with the secure computation with preprocessing, can you maybe give an overview from an implementation and framework point of view, which of those protocols that you covered in the past days are available in which kind of frameworks?
Right. So that's actually a slightly less satisfying answer, I think. So because this PCG stuff is all very recent, at least in terms of general MPC frameworks, they haven't yet been implemented to generate the preprocessing. So I guess for dishonest majority activity secure MPC, then the 2 big frameworks are Scale Mamba and MP Speeds. Both of these still use homomorphic encryption or OT directly to build multiplication triples. On the other hand, there are some implementations of at least the silent OT and vector OLE constructions based on LPN. So no, there's a couple of libraries like libote, Peter Rindle's library for OT extension, and then also what's it called, the EMP toolkit for general kinds of 2PC and MPC protocols like garbled circuits and secret sharing. They support the silent OT protocols and even vector OLE. But I think they haven't been plugged into the MPC protocols to exploit their full capability yet.
All right, thank you.
Okay. Thank you, Peter. Thank you for this lecture and for the 4 lectures you gave in the school. We enjoyed them very much, and I'm sure that they'll be very useful. I mean, they were very useful for me, and I'm going to go back to them and read them more, watch them more carefully. So thank you, and we're going to meet again at 3:15 Israel time for the next lecture.
Great. Thanks, Benny.
Okay. Thank you, Peter. We really appreciate it. You gave 4 lectures. That's quite a lot. Hello, everyone, and welcome back to the last session of our winter school. And we're going to have Rosario Genao again. He's going to start by continuing his talk from yesterday about discrete log threshold signatures. And then we'll move on to RSA-based signatures and quantum secure signatures. And Rosario, stage is yours.
Thank you, Benny. Thank you again for having me. Yesterday, if you guys remember, we had ended talking about the state of the art in terms of threshold Schnorr signatures. We had covered DSA, we had covered BLS, and we covered Schnorr. And this is a scheme where you assume dishonest majority, and the proof is by reduction, not by simulation, meaning that in the protocol, the adversary can bias some of the nonces and the keys that are generated by the protocol, but it doesn't really matter because with abort, and we are able in any case to prove that if the protocol doesn't abort, the protocol is unforgeable. So what I wanted to talk a little bit, the last thing that I wanted to discuss about discrete log-based schemes is that what's really challenging and is the design of a good, and I'll talk about what good means in a minute, DKG protocol. Remember, a DKG protocol is a protocol that established a random secret, which is shared among the players, and the corresponding public key, so if the secret is X, the corresponding G to the X is public to be used as a public key or as a public nonce in a generation of a signature like RSA or Schnorr. So the DKG protocol that we have talked so far had many drawbacks that prevent their implementation in large-scale networks. The first one is that they require like a synchronous network, at least the ones that I described. They have quadratic communication, not only quadratic communication in terms of communication exchanges private between the players, but also quadratic communication in the public channel that everybody has to listen to. So that's because every player sends out information that is linear in the size of the network and requires several rounds to end in order to resolve complaints, especially if you don't want to abort, especially if you want the protocol to have a successful termination. So the open problem is to design a truly scalable DKG. And let me give you a couple of slides on some of the progress that has been made in this on this area. So if you remember in the Feldman VSS and the Pedersen VSS, the parties check that their shares match the public commitments to the polynomial through a process of evaluation of the exponent. And then if those values don't match, then there is either an abort or there's additional communication rounds that are used to lodge a complaint, say, hi, my share doesn't fit into the committed polynomial, and then the dealer has a chance to resolve that complaint. So there is a notion of what we call publicly verifiable secret sharing, which says that it's possible to verify that the sharing has been performed correctly by everybody, not by the players individually checking that their shares are individually lying on the committed polynomial. And the way to do this, one general paradigm to do this is to use Feldman VSS. So you do a secret sharing, and then you do Feldman's VSS, and the only reason you do Feldman VSS is to have the public value G to the X public, and the commitment to the local share, the G to the X size. but then the shares are not sent through a private channel, which in any case it's very difficult to actually assume. But in reality, what happens is that the dealer encrypts the shares privately to each party with a key that each party owns. So the dealer chooses a secret, commits to the polynomial, to the sharing polynomial with Feldman VSS, and then encrypts every individual share with a public key that belongs to the individual player. At this point, what the dealer can do is a massive zero-knowledge proof that if you were able to decrypt the shares, then you would see that they lie on the polynomial uniquely defined by the Feldman VSS commitment. This becomes a publicly verifiable VSS because anybody can check that every player received the correct shares. So this actually not that difficult to do, and here everything that I'm talking about now is relative in what I mean by efficient but difficult. And if you use Payet's encryption, because by using the additively homomorphic properties of Payet's encryption, the zero-knowledge proofs right here are actually somewhat more efficient to build. And this gives you a publicly verifiable VSS, which, however, still requires a quadratic communication because the amount of information that every player reveals is still very large. So now, this is the reference to how to do this with Payet's encryption. Another recent work, and this is work from last year at Eurocrypt, is a really interesting idea to use aggregation. What do I mean by that? So if the VSS is publicly verifiable, and an example of that is the one that I showed you in the previous slides, then it's not necessary that every party sends their VSS out to everybody else so that everybody else can verify it. What we can do is, instead of broadcasting, we can gossip our VSS to a small set of neighbors around us. And then this gossip somehow keeps going around the network. But when you re-gossip the information that you received, you don't re-gossip everything, but you aggregate the VSSs that you received. And now you're saying, okay, I received the VSS for party 5, 7, and 9. I am not going to re-gossip the individual VSS, but I verify that they're correct. And I can do that because they're publicly verifiable. So I can verify that they're correct for everybody, not just for me. And then I aggregate, and what I gossip back out is this is a compounded VSS that includes the contribution of 5, 7, and 9. And at that point, as all these gossips keep getting larger and larger, you eventually end up with the aggregation of all the VSSs. And what's really interesting about this approach is that this yields a pretty large reduction in the communication between the parties. The unfortunate drawback is that they were able to construct such a DKG where the secret key, the only way that they were able to build this aggregation property was to create a DKG where the secret key is a group element, not a field element. And this happens in groups with bilinear maps where your secret key is a group element in the source group, and then your public key is a group element in the target group. And because the bilinear map is a one-way operation, then this works as a secret public key pair. So what this builds is a DKG which is unfortunately not usable for signature schemes that we know in that we use and know in practice, like such a DSA or Schnorr or BLS, because for those we really need a DKG where the secret key is a group element. But they are able to build a threshold verifiable unpredictable function, which you can think of it as a unique signature, which, if you're willing to depart from the use of standard signature schemes, depending on your application, if you're building an application from scratch and you're not necessarily bound to use Schnorr, you're not bound to use DSA, you can just put a new signature scheme in there, and hopefully you're not going to have any backwards compatibility problems with legacy schemes that use those old signature schemes. But in this kind of limited applications where we can deploy something new, this is a very interesting contribution. And by the way, this is the paper that, if I remember yesterday, I mentioned that one of the topics of yesterday was this difference between proof by simulations and proof by reduction, right? And if I remember, I told you that in our old paper, we said, well, all the Pedersen DKG allows you to do proof by reduction for Schnorr, but doesn't allow you to do proof by simulation for Schnorr or DSA or any scheme where you want to do proof by simulation. And we stopped at that. And we never really sort of formally defined what do you need from a DKG to have proof by reductions. And this paper actually did a pretty good job at the sort of formally define what are the properties of the DKG that you need to obtain proof by reduction on schemes that do have a reduction for unforgeability. Okay, and the last one, and this is the one that I'm most somehow interested in, the something that has been sort of occupying my mind for a while, is that if you can think of Feldman VSS as an example of a polynomial commitment, what the dealer is doing is, by publishing these values right here, it's really committing to the coefficients of the entire polynomial, okay? And you can say the same thing with Pedersen, right? And then this commitment right here allows you to efficiently verify that you received a good point on the polynomial. And why? Because you can do evaluation in the exponent, and then it's going to tell you this value right here is the correct evaluation of f at I, because if I put I in the exponent on this exponentiated coefficients, I'll get g to the xi. So it's a commitment where you can think of it as a commitment to a polynomial, where the opening is not to the entire polynomial, but the opening is to a particular point with a proof that this particular point is correct. The evaluation of this point is correct. And of course, the reason DKG has quadratic communication is that the size of this commitment is as big as the polynomial itself, right? And so the question is there a way to commit to a polynomial with a shorter string? And what I mean a shorter string, I mean both the commitment to the polynomial and the proof that this value is correct, which in the Feldman's commitment is the same thing. It's just the vector of exponentiated commitment, this vector of exponentiated coefficients. In that case, that serves both as the commitment to the polynomial and the proof. Is there a way to commit to a polynomial where the commitment and the proof of correctness are both strong, short? And by short, I mean sublinear in the polynomial, ideally constant, right? And in fact, we do have a polynomial commitment where this public commitment and the proof of correctness are actually constant size. However, they require trusted setup. And for those of you who don't know, this is a beautiful paper by Kate and al., where they use bilinear maps and the divisibility property of polynomials to show that you can commit to a polynomial with a single value, and you can prove the correctness of the polynomial evaluated at a certain point with, I think, one value as well. So with just one group element. This gives you a VSS which has much reduced communication, but it does require this trusted setup, which, by the way, has linear size in the size of the polynomial as well. So the interesting thing right here is that polynomial commitments have become incredibly important. This succinct polynomial commitment with sublinear parameters have become really important in the construction of snarks. And for those of you who don't know snarks, they're zero-knowledge proofs of arbitrary statements with small communication and ideally also small verification time. And some of these polynomial commitments exist even without trusted setup. They're not constant, but they do avoid the trusted setup. And the reality is that I am not seeing, and here I may not know of some work, and so if somebody knows of any of this work, I'd like to get a reference, but I haven't seen any of this other sublinear non-trusted setup polynomial commitment who's used them in the context of DKG. Because there too, they could substantially reduce the size of the communication between parties. And that, I think, was the last slide. So in terms of my target audience, which is, when I designed this lectures, in my mind, the target audience was graduate students who are getting into our research area. Here is a very interesting open problem in which a lot of people are working on, and where any contribution would be really has the potential of having a great impact. So to improve the efficiency of distributed key generation protocols, for example, the previous slide, if you could build disaggregatable, publicly verifiable DKG, but for field elements rather than group elements, I think that would be an incredible result and an incredible contribution. So, or if you could show how to build DKGs using sublinear polynomial commitments without trusted setup, that would also be very, very interesting. So before I switch gear and change topic, maybe if there are any questions about DKGs.
No, there are no questions as of now.
Okay, great. So let me switch to the other talk. Can you guys see the new slides? It says part 2.
Yes.
Okay, great. So now I'm done talking about the SQL log, and now I'm going to start talking about RSA. So the RSA signature was the first public key signature, and here I'm going to give you a brief tutorial on it. I mean, I'm sure everybody knows it in the audience, but let me sort of remind you. In RSA, N is the product of 2 primes, P and Q. The public key is N and E, and where E is a number which is relatively prime to phi of N. What is phi of N? Phi of N is the size of the multiplicity, the cardinality of the multiplicity group of elements modulo n, which is basically p minus 1 times q minus 1. So to find such e, it's usually not that difficult, and then you sort of invert the modulo phi of n. If you know the factorization of n, this operation is easy to do because you know phi of n, but we believe that without the factorization of n, we don't know how to do this. It's a conjecture. There is no known equivalence between the two. No, sorry, actually, I stand corrected. Computing d is equivalent to factoring because that gives you a multiple of phi of n, and that allows you to factor. What we don't know the equivalence of is the RSA operation, which is to compute d roots modulo n. This should say here, oops, this should say here modulo n. If given a number in Zn, to compute a d root modulo n is believed to be hard. And we know how to do if we have the factorization, but we believe that without the factorization, that would be not possible. So once to send a message m, you take you hash it and you compute m to the d mod n, and the verifier will verify by inverting the d root, the e root, and raising it to the e, and checking that the signature to the e is back equal to the message. This is the standard hash and sign RSA signature. We'll talk about different kind of RSA-based signatures later in the lecture. It's secure in the random oracle model, but we're going to try to figure out how to take the secret key and not have it sit in a single server and distribute it among parties so that compromise becomes difficult. So let's start with the very simple case in which we're going to share it among n parties, and all n parties need to cooperate to sign. And let's assume for a minute there's a dealer. Here, the dealer is unfortunately almost necessary. We'll talk about how to get rid of the dealer later in the lecture. But so what does the dealer do? The dealer generates the whole key pair for RSA. So it generates N, E, and D. And then, and here I'm denoting with capital N the RSA modulus, and with little n, sorry for the confusion, the number of parties. Then it takes the secret D and shares it among the n parties additively. What does it mean? What do I mean by that? It chooses random shares in modulo phi of n, which the dealer knows because the dealer knows the factorization. And it chooses them at random under the condition that their sum modulo phi of n is equal to d. Again, the dealer can do all of this because the dealer knows the factorization. At this point, to sign is actually not that difficult because notice that to learn D, you need to compromise all the servers. Do they play the players signs? They sign using the homomorphic property of exponentiation. Each player reveals a partial signature, which is m to the di, where di is his local shares. And then obviously, that the real signature is the product of all n signatures modulo n, because remember that because phi of n is the cardinality of the multiplicative group modulo n, the exponents work modulo phi of n. So this should be pretty simple. But the proof of security is already using a very subtle issue. And the issue here is that the parties see random numbers chosen in z to the phi of n. And remember, phi of n is something that not only the parties don't know, but they're not supposed to know. If the parties learn phi of n, they will learn the factorization of n. And what happens here is that the parties are seeing a distribution of numbers which is in in 0 phi of n. And the question is, do seeing numbers distributed uniformly from between 0 and phi of n, does that give you any information about phi of n? So, okay, let's prove how this works. It's basically the same interpolation in the exponent argument as is in the case of discrete log scheme. What the adversary is what the simulator is gonna do is gonna give random DIs to the adversary, and all that thought there about what I mean by random. And now, if the simulator has the real signature, given the real signature, it can compute the partial signature of the honest players by taking this equation right here, right? And he knows the partial signatures of the bad players because he's given them DI. He knows the signature S, so he can just go and choose the partial signature of the honest player, so that random condition that they multiply to S. So the question is, where are this DI chosen? From where? The simulator does not know phi of n, so it can't match the distribution that the dealer gave to the real dealer gave to the parties. So the reality is that the simulator chooses them in Zn. And the reason is that n is a very good approximation of phi of n. In fact, the uniform distribution between 0 and phi of n and the uniform distribution between 0 and n are indistinguishable. That is true when P and Q are somewhat of the same size, which is the case when you choose RSA modulus. So, and so this is the subtle issue that comes up when you do additive n out of n RSA signatures. The subtle issue that you don't know phi of n will continue to haunt us and give us trouble throughout the entire set of lectures that I'm going to do about RSA. So let's try to move to threshold. So what if we want to do Shamir over a ring? So the dealer can still share the, remember, why do I want to do this over a ring? Because now we're working modulo phi of n. Phi of n is not a prime, so we're not guaranteed that you can do inversions, first of all. But if we don't know phi of n, we cannot do the inversions. The only way we can invert modulo phi of n, multiplicative inversion, is if we know phi of n. So, okay, so let's see what can we do then. So we choose a random polynomial, f of x, such that f of 0 is our secret, which in our case is the exponent d. So then the dealer, who knows phi of n, sends the shared di to the player. And now the problem is that the set, if you have a set of t plus 1 players, polynomial interpolation doesn't work. And it doesn't work because the Lagrangians are fractions. Remember last time we said to do polynomial interpolation, you need a field because you need to be able to compute those inverses. And to compute the inverses, in this case, you need to know phi of n. Phi of n is secret. So, and if the participant knew phi of n, they would know the factorization, and so the secret key would be d. So what can we do? Remember that the polynomial interpolation formula says that d is equal to the linear combination of the di with some Lagrangian coefficients. And remember that the Lagrangians have this form right here, right? And let's assume that this number right here is invertible, modulo phi of n, which means that this number right here does not have factors in common with phi of n. So if you assume that I and j are small, because those are numbers between 1 and n, your number of participants, you want actually phi of n not to have small factors, except for 2. So you're going to have somehow the you get rid of the 2 by multiplying by 2, and then you have all this stuff right here that will be, you can assume that this stuff right here is invertible modulo phi of n. What the players, however, can do is remove this this denominator from the computation of the Lagrangians by multiplying d by the factorial of n, because the factorial of n has all the numbers that appear and more, but it definitely has all the numbers that appear in this denominator. So if a player reveals, instead of revealing di, a players reveal n factorial di, the interpolation formula will work because all the denominators are cleared, but what you end up computing is not d, but n factorial times d. Is that clear? Any question at this point? So now the question is, what are we going to do with n factorial times d? So let's do our first attempt to build t out of n RSA signature. And I say first attempt because there's going to be an issue with this one. So, okay. So now we're going to do this Shamir secret sharing of d that I just showed you. So the dealer generates the RSA key, shares the secret key d among the parties with this Shamir secret sharing over phi of n. So, and let d1, d2, dn be the shares that the dealer gives to each party. Then the signers reveal si equal m to the di mod n, right? And now remember, we're going to take this di and raise it to the n factorial so that the n factorial multiplies the di, right? So instead of raising it to, so we're going to take s, we're going to compute s to the n factorial. How? By taking the si and raising them to n factorial times the Lagrangian, right? N factorial times the Lagrangian now is an integer, and so we can do this computation right here, and this will give us m to the d times n factorial, okay? So we didn't get the signature, we get the signature raised to the n factorial. But we want the signature. How do we get the signature out? Let's assume that the GCD of E and n factorial is equal to 1. And you can do this because you can choose E to be bigger than n, you can choose E to be a prime, and then this works. And then you use the extended Euclidean algorithm to compute A and B such that A times C plus B times n factorial is equal to 1. And then this is a very famous, it's referred universally as Shamir's trick that allows you, given s to something which is relatively prime to the public RSA parameter, to compute s. And how does that work? So what is s? S is m to the d, but I can multiply this d by 1. And 1 is a times c plus b times n factorial by the GCD property. And now look at what happens when you split this sum as a product. The d and the e cancel out, and so you're left with m to the a. And what about the other one? The other one is m to the d times b times n factorial, right? But m to the b times n factorial is the signature to the n factorial, which I just received from the players. So I am going to, sorry, this should stay here, s to the n factorial. But I have this component right here, and I raise it to the b, and I have this component right here, and I raise it to the a, and I have my signature s. Okay? And this was there were other, this was a very interesting story about this paper by Victor Schuch, that somehow this very simple observation had escaped lots of people who had worked on threshold RSA, and up until 2000, people were using different algebraic structures to get to somehow get rid of this problem with the Lagrangians. And in reality, with these assumptions about the set of participants and the prime, you do get a pretty easy solution on how to compute the signature. Okay, so what did I say first attempt? Because, so remember here, the player broadcasts them to the DI, and then we get rid of the denominators by taking this partial signature, and instead of raising them to the Lagrangians, by raising them to the Lagrangian time a factorial number. Turns out this is not enough. Let's try our typical simulation with our by now standard 2 out of 5 network. So the adversary controlled 2 players, and now we have a simulator. The simulator gets N and E and starts a network where the simulator plays the 3 good players and the adversary plays the 2 bad players. Remember, how does the simulator simulates the sharing of D? It's just going to give random integers between 0 and N to the to the adversary. Okay, then the adversary says, please give me the signature for a message M. The simulator goes and asks its oracle, and the oracle gives it M to the D. So now the simulator should come up with S1, S2, and S3, right? So, well, the simulator knows M to the DI for the bad guys, because he knows DI. The simulator knows M to the D. So he knows 3 points in the exponent of this polynomial of degree 3. So when we were working modulo a prime, we were going to just do interpolation in the exponent to get the remaining partial signatures of the simulated honest players. But here we cannot do it, because again, we run into this issue of Lagrangians, right? And we can interpolate, once again, the Sj raised to the factorial, right? We could do that, but now we don't have a matching EI that would allow us to do Shamir's trick here. We do interpolate this J to the N factorial, but that doesn't give me Sj, which is what the protocol does. Remember, the protocol reveals the regular partial signatures and then gets rid of the fractions when you interpolate. But here, we're not able to get those regular partial signatures. Any questions? We have another fraction that comes in. So, yeah.
We do have a question regarding the n factorial in general. What if like n is large, say like n is 100? How do you work with n factorial?
Very good question. Hold it, and we'll I'll get to it in a minute. Okay. Yeah, it is an issue when n is large. This is a very big issue, particularly because when you raise to the n factorial, you can't take n factorial mod phi of n because you don't know phi of n. So you have to raise to the n factorial as an integer. So that is a very good question, and it's coming up in a couple of slides. But right now, I hope you all understand why this scheme where you're revealing just the basic partial signature gets stuck in the simulation. So here is what we're going to do. What we're going to do is that the players do not reveal m to the di, but they reveal m to the di to the n factorial. Why? Because I just showed you that that's what I can simulate. Okay, so now then I do my interpolation. Again, I have to multiply to the n factorial to get rid of the Lagrangians. So what I end up with is the signature raised not to the n factorial, but to the n factorial square, which makes things even more complicated with respect to the questions that we just had. But we're going to do the GCD trick again, assuming that z is still, obviously, if n factorial is relatively prime to e, then z is also relatively prime to e. Okay, so clear what's going on now? Now n factorial comes twice. Comes in the exponentiation by the players of their partial signature and in the interpolation. This one right here, we needed to make the interpolation possible. And this one right here, we needed to make the simulation possible. Okay, and now the simulation is going to work. Remember again, where the bad guys have random shares, the simulator on input on message m gets a signature from a centralized oracle, and now the simulator computes the modified partial signatures. Did I miss an n factorial here? I think I missed an n factorial here. It knows this one right here. Oh no, the modified partial signatures, I mean the actual ones with the di, without the n factorial. So those are not the real partial signatures that the protocol defines. Those includes the n factorial. So I gave them a new name, UI. The adversary knows these values. It knows this value because it gets it from the oracle. It knows these values because it knows the di. And now it can interpolate in the exponent by multiplying by n factorial. And that gives him exactly m to the di to the n factorial, which is SI. So now by defining the partial signatures as m to the di to the n factorial, we're able to get the simulation to work. Any questions? And then, of course, there's a final part in the simulation, which I'm not showing, that at this point, the adversary is seeing the same view that he would see in a real execution, and therefore it will forge with the same probability as it will forge in the real execution. And if it forges, then the centralized simulator forges in the centralized. The simulator forges in the centralized scheme, which we assume to be impossible. So and this is how the Shoup threshold RSA works. And here is the question, here is where we're going to address the question that just came up before. In the previous solution, the value n is a parameter to the scheme. This is already, it requires parties to do computation which is linear in n. And why? Because you have to exponentiate to n factorial. And again, you have to exponentiate to n factorial, where n factorial is an integer. You're not going to be able to reduce n factorial to the size of the group n, because you don't know phi of n. So one issue is, what if n is really large? Yes. The other issue is that you are putting this very strict coordination in the network that players are exactly identified with the integers between 1 and n, right? There is nothing in anything I've said so far, I've used the identifiers I to be between 1 and n just for convenience. Everything I've said so far works even if the identifiers are your MAC address, the hash of your email address. You can use any unique identifier. As long as players have unique identifiers, you can use the unique identifier as the evaluation point for Shamir secret sharing. It doesn't have to be I. I assumes the specific coordination in the naming space, which may not be possible if you assume like what I call here ad hoc groups, where people come in, come out, they come in with this identifier, which is like their network identifier, and so on. So if your identifier is a k-bit string, then now we're going to have computation which is exponential in k, because n factorial becomes 2 to the 2 to the k, right? Because I had to assume all possible identifiers, and that is just not going to work. So where is the factorial coming in? The factorial comes in two places. One is when we interpolate, right? To remove the Lagrangians, the denominators from the Lagrangians. The other n factorial comes in when I reveal my partial signature, and this one is really an artifact of the proof, okay? So let's look at the two of them separately. So the one in the computation of the signature can actually be somehow compressed. You don't really need to use n factorial, right? You know the parties that are participating in the computation of the partial signature. You say, oh, this t+1 parties come in, you add their t+1 identifiers, and so you can replace it with rather than with the n factorial, with the LCM of all the denominators that appear in this in the Lagrangians, in the proper Lagrangians. And here I'm using I minus j, but again, this could be the identifier play I and the identifier play j. Okay? If your identifiers are up to 2 to the k, then this number is going to become much smaller. It's going to become 2 to the k over t rather than 2 to the 2 to the k. So this is actually a very almost trivial observation. The issue is the one in the reduction. The one in the reduction is an artifact of the proof, which means in the real execution of the protocol, I cannot assume that I know what is the set S that's going to come in the reduction of this. You know, it's basically the set of the bet players, right? And that is, again, I would have to know in the course of the execution of my protocol who the bet players are in order to do something like this. And that, I don't know. So I don't know how to remove this n factorial. And let me tell you again, pictorially. So remember, the simulator can compute these guys, but so it doesn't know how to compute. To compute this guy, he would have to do this n factorial trick. But to get rid of this denominator, which is a denominator, the ZA, which I'm going to call ZA, which is the product of all the denominators of the adversarial Lagrangians. Now, if I knew, actually this could be the LCM, not really the product, right? So if I knew ZA, then I could do the same trivial trick that I showed here. If I knew ZA, so instead of raising to the n factorial, sorry, I would raise it to the ZA, and the simulation would go through. But I don't know ZA. So in the simulation, if I don't want to use n factorial to cover all possible ZAs, I would have to compute the ZA root in order to really compute the Lagrangians in the interpolations. So here we're stuck, right? So the only way we were able to prove this was by introducing an extra assumption on the security of RSA. And the assumption is that when you start the game, instead of having this game right here where the simulator sends a message M and you get back a signature M to the D, the simulator is allowed to also provide the challenger with an exponent of its choice, which then it will get not just M to the D, but it will also get the ZA root of M. So it gets at the E root of M, but also this additional root of M. And what we conjecture is that if E and ZA are relatively prime with each other, this is not going to help you find E roots, okay? So now, if we're having this nice, helpful challenger here, then we have the information that allows us to complete the simulation. So this threshold RSA, where you raise to the factorial, you can remove the factorial in the partial signatures if you assume the stronger version of the RSA problem, which, by the way, in the random oracle model where ZA is actually is equivalent to the regular RSA, or you have to put the factorial in, okay? So we deal with this factorial by adding this extra assumption, and we remove one factorial, and the other factorial we compress it simply with the right multiplier, which is the LCM of the players who are reconstructing the signature from the partial signatures. Any questions so far? Okay. So everything I've told you so far works for honest but curious players, which always output the correct partial signature. Now the question is, how do we detect bad partial signatures? Because even a single partial signature would prevent us from, well, one is actually not bad because you try all possible subsets until you find the signature that verifies. But again, remember this, for T bad signatures, that would give you an N to the T algorithm, which may not be practical. So I'm going to show you two ways of detecting partial signature, bad partial signature. And the first one is based on message authentication codes. So at the beginning, the dealer, when the dealer sends a shared DI, the dealer also chooses triplets, AIJ, BIJ, and CIJ, such that A times DI plus BIJ is equal to CIJ. And this, for those of you, many of you may recognize this as the universal hash function based authentication code. We need to do this over the integers. Even if the dealer knows phi of n, he's going to choose AI and BJ. So he's going to choose AIJ and BIJ on sufficiently large random integers, and then set CJ this way also over the integers, okay? The reason that the dealer is going to do this over the integers is that he's going to send CIJ to player I together with his shared DI, and AIJ and BIJ to player J, okay? Now here you see why we have to do this computation over the integer. If he had done this computation modulo phi of n, if I and j, since it's giving this to every pair of players, if I and j are both corrupt and they collude and they pool their information together, this equation right here, if done modulo phi of n, would give them a multiple of phi of n. Multiple of phi of n is equivalent to factoring. So the dealer has to do this over the integers. Now, when the player I outputs the partial signature, is also going to output m to the cj. And it does this so that player j can verify that the partial signature is correct, but verifying the message authentication code in the exponent right here. Okay, so the player j accepts this partial signature if this equation right here verifies, which is the message authentication code. This is an information theoretic message authentication code, and it will work in the exponent because it's a linear operation. To what I'm not showing you in the slide, you can go look at the paper, is that A, this is still a good message authentication code, even if I do it over the integers. And this depends on how big you choose these parameters. And B, that while this is, if you do this modulo prime, this is a one-time message authentication code because it, once you use it once, it's done. You can use it again to authenticate a different message. But here, it allows us to, because what changes is m, it allows us to use it several times for every different m because we're doing it in the exponent. And basically, the algorithm that would help you break the message authentication code, if you use it more than once, you can do it because it's hidden by the modular exponentiation, which is a one-way function in the RSA one-way function. So those are the two technical issues in this solution right here, that the code has to work over the integer and that this equation allows you to do it repeatedly. So this is the first one. The other one, and then I think would be a good place to stop, is to use zero knowledge. Zero knowledge, we do that by the dealer is going to augment the sharing phase by publishing a public commitment to the partial share. So G to the DI will become a commitment to DI that everybody knows. And remember that the partial signature is M to the DI, right? So this is if you do our things where we remove the n factorial, but even with the n factorial, you can put the n factorial in both of them. It doesn't matter. What matters is that what is necessary is that the player has to add a zero knowledge proof that SI and GI have the same discrete log with respect to M and G. This requires, one technical complication is that it requires restricting everything to a cyclic subgroup of Z and star, which, for example, of sufficiently large order. And for example, if you use safe primes, that could be the subgroup of quadratic residues. Okay, so what are these proof of knowledge, the zero knowledge proofs for groups of prime order where there's some really, so we need them in groups of unknown or unknown composite order, but let me show you first how they work in groups of prime order, and this is very old work by David Chow. One is basically a duplicate of the Schnorr proof. I'm going to send you, remember I have to send you that y is equal g to the x and s is equal m to the x. I'm going to send you g to the r and m to the r. You're going to send me a challenge, and I'm going to open a linear combination of the secret and the random nonce, r plus cx mod q, and you check two Schnorr equations with the same things, because you're using with the same things, that guarantees to you that the x is the same across. This is a public coin proofs, can be made non-interactive with via Shamir. It also very nice property is that it's a proof of knowledge of X. Another one is a secret key coin in which the verifier chooses A and B at random and sends G to the A, M to the B, because the prover will respond this with C to the X, and the verifier checks that the C to the X is equal to Y to the A, S to the, this should be B right here. And that guarantees that Y and S have the same X as the exponent, because the prover has no information about A and B. This is a private coin, cannot be made non-interactive. It's a 2-round honest verified zero knowledge. You can turn it into 4-round full ZK by standard techniques. How do you do this with a known order? The first one, instead of choosing R remember, you don't know the order of the group. So you're going to choose R in a pretty large set, maybe slightly bigger than that. And the challenge is going to be in an integer set as big as your security parameter requires, because this is where your soundness level is decided. And then you answer, but where in the Dasku log case, you will know the modulus, and so you would take this equation modulo Q. Here, you want to take this equation over the integers. And that's why you need to choose R large enough. And then the verification equation remains the same. So you choose R large enough so that this answer right here statistically hides X. In fact, you can prove that this is a statistically zero knowledge proof. The other one, you don't even need to do that. You choose A and B in Zn simply because you don't know phi of n, but it's enough to choose them in Zn, and the proof proceeds exactly as Chow proof. So, okay, and that's, I guess this is a good place to stop, because now we're going to change topic. And once you detect who's contributing bad shares, you kick them out. You have enough good shares, and you can, if you have enough good shares, then you can reconstruct the signature. So, and I think this is a good place to stop.
There's one question.
Yeah.
When we use threshold RSA, it would likely be nice to have a distributed protocol for generating the public key.
That's the next.
Okay. The question was: are there any practical protocols that also do it in such a way that you have safe primes?
I think is Commit here? I think she's the right person to answer that question. I know that there are protocols that give you Blum integers. That is not difficult to do. And by the way, for what I just told you, I think Blum integers are sufficient. You don't really need safe primes. It's to have the quadratic residues being a large subgroup. I think it's enough for your integers to be Blum integers. But I'm not sure. I suspect not, but if Commit is here, she can probably correct me. I don't think you can have the distributed protocols give you safe primes. We'll talk about the distributed protocol after the break, but
and with regards to the zero knowledge proof here, can the size of the R in the zero knowledge proof be reduced by doing something akin to the Fiat-Shamir with a Bard's approach for lattice signatures?
No. So the size of R is really so. Your size of R has to compensate, first of all, for CX getting bigger, right? So, and then of course you can choose a smaller C, but that would give you a smaller security parameter, right? So the size of R is really required to be an order of magnitude bigger than CX, so that the noise of this randomness completely overwhelms whatever information you have about X. What you want is that this value right here looks like it's uniformly distributed no matter what X is, right? Because in the simulation, that's what you're going to do. You're going to choose D at random, and you're going to work backwards, right? You're going to choose C at random, you're going to choose C at random, and you're going to set A and B according to these equations. Think about the interactive case, right? So then we're random where? Random where you're going to choose your interval this big, and if you choose the same D in the same interval, if Cx is relatively small to this NB, the fact that you're adding Cx is not going to mess up the distribution too much. That's basically what the proof is. So I don't think that using Fiat-Shamir will help you reduce the size of R. And by the way, these are all efficiency concerns because these are all exponentiation that you have to do with this integer, right? You can't like reduce it in any way.
Okay.
Okay, so thank you, Osayo. I also have a question.
Yeah.
Are there applications where they prefer to use RSA signatures and not discrete log-based signatures? Because they're much more complicated to use in threshold.
Right. No, so the only thing that I can think of is certificates, right? And because those are like if you think about all the applications like blockchain application and all of that, you have BLS, you have DSA, those are much shorter. First of all, they're much shorter signatures than RSA, so people use those regardless of the threshold, and then the threshold is also easier, right? So when we did RSA, it was back at the time when we were working on thinking that certification authorities were going to maybe use these things. And no, I don't know of any application that uses specifically RSA signature in threshold fashion, partly because of the. So actually, the protocol itself is not that complicated, except that you need the issue is the key generation, which we're going to talk for a minute. And in fact, the main motivator for the distributed key generation is really not RSA signatures. It's more distributed Payet decryption. But we can talk about that later.
Yeah, I guess it matters for backwards compatibility if you need it. Yeah.
Right. So if you have a system where you're signing with RSA and you don't want to change it and you want to protect your key, you can do this. And again, remember, a one-time dealer, the shares in some circumstances may not be like an issue, right?
Yeah. Okay. Thank you.
Sure.
Yeah. And we'll be back in 15 minutes. Hi, welcome back. And we're here for the last hour of Rosario's lectures about threshold signatures.
Okay, thank you. Before the break, we had just finished talking about the equality of discrete zero knowledge proofs for groups of unknown order, which we use to remove bad partial signatures. So now we're going to talk about, again, how do we generate RSA keys without relying on a dealer. Remember, if our goal is not to have single point of failures, then this RSA key should be generated jointly by the parties rather than having a dealer know the key, even if it's a single point of failure, which is somehow limited in time to just the key generation. Now, if DKG is already the sore point when it comes to discrete log, it even so more a problem when it comes to RSA. And the reason is that removing the dealer is not as easy as in the case of discrete log base key. Here, the dealer is not just generating a random value. It generates two random primes, multiplies them together, keeps the factorization secrets, and then he has to generate the values C and D. To replace the dealer, we have to come up with a protocol that does all of the above with the secrets shared among the players. Now, in principle, you could use an MPC protocol, but because we know that MPC can do anything, but this would still be a pretty difficult task to perform efficiently, because if you think about how centralized RSA generation works, you select a random prime, you run the Miller-Rabin primality test until you select a random number, you run the Miller-Rabin primality test until you find the prime, then you do it again, and then you multiply the two primes together. The bottleneck to do this distributively would be really the Miller-Rabin test. And that's because the Miller-Rabin test perform several modular exponentiations, and you would have to do this modular exponentiation in a distributed way. So we're going to see how the biggest contribution here is to move, is not that you're going to do less modular exponentiations, because then you will get a better primality test, right? But what you're going to do is remove the modular exponentiation from the distributed computation, but move them locally to each player. And that's going to be the biggest advantage on how to do generation in a distributed way. This has been a very active research area in the last, I think that every year in the major conferences, there is a paper getting some improvement on this. As I was saying before the break, the motivator for this hasn't really been threshold RSA signatures, as much as the distributed generation of an RSA modulus for a Payet encryption scheme, which uses also the factorization of n as a secret, because it allows several MPC protocol to run faster if you have a shared Payet key among the players. In fact, I didn't talk about that yesterday. There's even a paper that you can do threshold DSA much easier if instead of having individual Payet key to do that MTA, you actually share them among, you have one with a shared decryption key among the players. So this goal goes back to this seminal work by Dan Bonnet and Matt Franklin on how to generate RSA keys in shared form. And as I said before, the biggest goal there is to avoid using the Miller-Rabin probability testing. So let's think about how, let me break down in phases how the Bonnet-Franklin scheme works. The first task is that the parties will generate together a random number, and then we'll do some very simple preliminary sieving to make sure that it's not divided by small primes. And this is just to avoid doing the more expensive steps that come later too often. Then, say that we have two numbers that have passed this preliminary simple sieving step. Then you multiply them. So P and Q, they'll be in share form, and I'll get into the details more in a minute. But the parties will multiply and get N. And now the test is going to be on N, which is public. This test is not going to be that N is prime, but that N is bi-prime. But bi-prime, we mean the product of two primes. Now, if this test succeeds, this is a randomized test. There's false positive cases. But if the test succeeds, then we assume that N is bi-prime. And then at that point, the parties compute E and D. OK? So those are the steps. And now we are going to slowly go one by one. So the sieving and the multiplication are actually not that complicated. So, and I'm going to really hand wave a lot of it, because otherwise we'd have to do an entire hour on the Bonnet-Franklin paper. But the paper is, it's actually really well written, and it's pretty easy once you have this roadmap to sort of understand it. So I would encourage you to read it. Because it is, by the way, the basis of all the papers that came later. Every paper that came later is just follows this roadmap and just optimizes each of these individual steps one by one. So let's start with the first steps. So what do the parties do? They generate a random number, and for the moment, let's just assume that we're in an N out of N scenario. You can do all of what I'm saying with Shamir, but let's just for simplicity do N out of N. So each party generates random numbers, PI and RI, in PI in a certain bound, which is the bound of the size of the prime numbers that you're interested in. And RI has to be a slightly larger bound, because it's going to ask as a mask, act as a mask that will mask P when we reconstruct PR. Okay, so again, we have PI, which is shared additively among the players. So P is the sum of the PIs, R is the sum of the RIs, and if you remember, we have to reconstruct the product. You may want to remember from yesterday that we do have a way to do this through pairwise multiplication and all this thing of changing multiplicative shares into additive shares. Actually, when Bonnet-Franklin did this, they used something different, but then this is, you can do it with the MTA protocol, which is exactly what then later Gilboa did for the two-party case. Okay, then the next step is that you want to sieve, right? So for every small prime that you want to sieve, you reject P if PR is equal to 0 modulo A. Why? Because if PR is equal to 0 modulo A, that means that A must divide PR. And if R is pretty large, then the chances that A divide R is probably not that large, and so there must be that A divides P, right? Again, probabilistically, so that will, you may reject a good P, but most likely you're going to reject a P that is divided by A. And you do this for a bunch of primes up to whatever bound you're interested in. So, sorry. So let's assume now that we have passed our test, and now given two such numbers P and Q, remember P is additively shared, Q is additively shared. the party reconstruct the product. Again, this is the multiplication additively shared values. We know how to do it, at least in principle. So, okay, so we have now an n. What we know about this n is that p is the product of p and q, and then p and q are not divided by small primes. Now we want to make sure that p and q are really primes. So here I'm going to show you a very simplified version of this test. It's called the Jacobi test. So if n is the product of two primes, then phi of n should be p minus 1 times q minus 1 should be the order of z n star. That is not true if n is not biprime. That's basically the idea of this test. So what are you going to do? Well, remember that the parties have an additive sharing of phi of n. Why? Because they have additive sharing of p and q, and they have n is public. So all they have to do is use their local shares on p and q to get an additive share of phi of n. So for example, if the first player will put n and 1 in its shares, and all the other ones will use p1 and q1, okay? And now you're going to repeat many times that you choose a random value g, and you test that g to the phi of n is equal to 1. And if that's the case, then you are going, actually you have to do p plus or minus 1, but basically this tells you that phi of n has to be the order of the group. Okay, this I'm hand waving, I'm trying to get you the concept across. There's very subtlety there, but this is the basic idea. Now, here is where the things get very interesting. To do this test, the exponentiation has to be computed locally. All a player has to do is take g and raise it to the phi, and this gives you gi, and then you cannot reveal the gi, so you have to do a distributed computation to check that this product is equal to 1. You're revealing the gi will probably give you information that you don't want to reveal. Okay, so notice that the whole advantage of using this biprimality test is that the exponentiation is being pulled out of the distributed computation and is done locally by each player. Okay? There's also an additional GCD test that is required, which basically checks that n and phi of n are relatively prime, and then once you've done all of this thing, you have this probabilistic guarantee that n is the product of two primes. Now you're left with the inversion of our shared sequence. And here I'm going to show you not the protocol that is in the Bonnet-Franklin paper. I'm going to show you a different protocol that I wrote together with Dario Catalano and Shaya Levy later on. It's more efficient than the Bonnet-Franklin at the expenses of yielding slightly larger shares of D, which that would give you some sort of inefficiency later when you want to sign with this D because they're bigger. But the protocol itself is much simpler, not just computationally, but also conceptually to explain. So I chose to show you this one. So, by the way, so what do we want to do? We have n, we have phi of n, which is shared, and we have E, which is public. E, you can choose, you choose a prime, you choose, and so you're fine. So now, you make sure, so now we want to make sure that we want to compute a sharing of D. This is the dual problem of the one that we saw yesterday for the case of DSA. In DSA, we had a public modulus, and we had to invert a shared secret. Here, we have a public value to invert, but modulus a secret value. Okay, so you see the difference between the two. So how are we going to do this? The parties have an additive sharing of phi of n. And so what they're going to do, they're going to choose a random value in a large enough interval, again, and this is in additive shares, again, and then they'll reveal this value right here, phi I plus ERI, calling AI, and set A the sum of the AIs. Now, if you do this, obviously, what are you going to get? The sum of the phi I give you phi of n, and the sum to the RIE gives you RE, right? And here is why you want to choose R large enough, because this is going to be good enough. Everything is over the integers, so if R is large enough, this value hides phi of n statistically, and so we are not revealing any information about phi of n. Another disadvantage of the Bonnet-Franklin protocol was that it was revealing a few bits of phi of n, not many, so it wasn't much of an issue, but here we reveal nothing. So now, if the GCD of A and E is equal to 1, then there exists B and C such that A times B plus C is equal to 1. Okay, so let's see what that gives us. So 1 is equal to A, B plus C. But what is A? A is phi of n plus RE. So if you plug that in, you get B phi of n plus BR plus C times C, right? You're going to take this BR and put it in here because there is the E in front. Okay, takes this equation modulo phi of n disappear, and you're left with 1 equal BR plus C times C, which means what? That BR plus C is the inverse of E modulo phi of n, which is exactly what we were looking for. And here you see why you're getting a D, which is somehow a bit large, because you want this R to be substantially large than phi of n, right? So you're going somehow an order of magnitude, probably the size of n square, to get your statistical secrecy, which makes your shares of D somewhat bigger, right? Because now you can set your shares of DI to be just there should be a C in there, right? BRI plus C, obviously. Well, I think C goes only in the first party, so you're right. So C goes, one party adds C and the other guys put BRI. Any questions? So this is basically the bare bones explanation of how Bonnet-Franklin works. So, by the way, allow me a little detour, which tells you why we did this, even after. So we did this work after Bonnet-Franklin appeared. So there was already a protocol for this. Why didn't we like the protocol that Bonnet-Franklin had? The reason was that we looked at this problem for in the context of thresholdizing other signature schemes based on RSA, which are the signature based on the strong RSA problem. So far, when I talked about the RSA signature, I've been talking about the basic hash and sign, which is proven in the random oracle model. There are actual other signature schemes which do not rely on the random oracle model, and they're provably secure based on the strong RSA assumption. What is the strong RSA assumption? Is the one in which instead of giving you n and an exponent, I give you n and a fixed group element, and you are allowed to choose the exponent for which you're going to get E roots. So the adversary is allowed the choice of the exponent E, and then is able to compute E roots with that exponent. We believe this E roots of this fixed base. We believe this to be a hard problem. And the signature schemes, I'm not going to go into full details of the signature schemes based on this, on the strong RSA, but they both work with this idea, which is that the public key is this n and this fixed base, and the secret key is phi of n. The message m is mapped into an exponent m, and the signature is the m root of G. where M varies with every exponent. And this sort of tells you why you need the strong RSA, because now the message is under the control of the adversary, which means the exponent is under the control of the adversary. And remember, we don't want random oracle, so you can't say, oh, the message is mapped into a random exponent. There are two ways. One is the message M is mapped through a deterministic function that output primes into M, and the other one is a randomized, where from every SHM you select a random prime in some way. So, and at this point you can verify by checking that S to the M is equal to G mod M. And these are the two schemes that I know of. One is, the first one uses this deterministic mapping of M to the exponent, and the other one uses a probabilistic generation for this exponent. And to make the schemes into threshold ones, we need exactly the protocol that we showed before. Computing the sharing of the inverse of M, where M is public, but the modulus is secret and distributed. And one reason we didn't like the Bonnet-Franklin inversion protocol is that it leaked those bits of phi of n on. And while it is okay to leak a couple of bits of phi of n once when you're generating n and then you're done, because you can always guess those few bits, it wouldn't be okay to leak bits every time you sign. Then you probably risk leaking too many bits about phi of n and breaking the scheme. So we wanted something that leaked nothing, and that's why we went back to the drawing board and didn't use the Bonnet-Franklin modular inversion protocol. Turns out that the protocol is even simpler at the cost, as I was saying, to give you a slightly larger D compared to the Bonnet-Franklin. Any questions so far?
No questions so far.
So this, I gave you the bare bones version of the Bonnet-Franklin. Let me tell you, I gave it to you in the n out of n case. If instead of using n out of n sharing, additive sharing, you use Shamir, it still works. You require honest majority for those multiplication protocols that I told you about, in which I sort of say, oh, you have the shared values, you gotta multiply them. And it was only proven for the honest by curious setting. So there were several papers. The first follow-up paper was actually this paper by Gilboa that shows how to extend it for the two-party case, which is exactly where this MTA protocol that we discussed yesterday was introduced. There have been many follow-up works, and I'm not going to get into them because they've all, again, it would take me the entire 4-hour school to cover them. I don't think Kermit is here today because she would be the perfect person to present this, since she's been very active in this area. But so there have been many protocols that have been presented following the Bonnet-Franklin approach, but they all follow this basic blueprint that I showed you. And the improvement have been focused on, the first one is getting a better seeding at the beginning so that we can avoid running the biprimality test too often. Reducing the communication complexity. For example, the last paper by Kermit and their co-authors uses a distributed version of the MTA protocol where the additively homomorphic encryption is not, there isn't one for each player, but there's a single one which is with a distributed decryption key. But this is sort of like a circular problem, because if you use Payet, then you would need a distributed generation of RSA to have this distributed Payet, right? So they don't do that. They use a lattice-based additively homomorphic encryption scheme and use that to give you the threshold version. And we'll talk a little bit about the threshold and lattices in a minute. And then there is a lot of works that have been adding the security against the malicious adversary just by adding the appropriate zero-knowledge proofs in the various steps. The first paper that did this was a paper by Frankel, Young, I'm not sure, there was somebody else in that paper. The last paper by Carmita and co-authors uses recent advances in SNARKs, which are important because they have sublinear size proofs. So they reduce the communication a lot, and in some cases also sublinear verification time, which reduces the amount of computation that each party has to do. So again, this is not the only paper. There was another paper last year also, which I really liked, which was this, the beautiful title was The Return of Aristoteles. Again, focus on doing much better sieving to reduce the overall complexity of the scheme. And also they use a different way to enforce security against malicious adversary, which somehow reduces the use of zero-knowledge proof. They do this consistency checks where they reveal things that are going to be wrong if the adversary has been malicious, but at the same time don't reveal any information about the private values of the players. So lots and lots of interesting optimization, but overall the paradigm remains the one of the Bonnet-Franklin scheme. The bottom line is that we can now generate distributed RSA model I for thousands of parties in a matter of minutes. This is what the numbers that were reported by this paper that I had referenced up there. As I was saying before the break, threshold RSA signatures is not really the main motivator of this line of research. The ability to have a threshold version of the Payet encryption is really what's been motivating this this line of work, because that would give you more efficient multi-party computation protocol in general. So I think I'm done with RSA. If there are any questions, I'll take them now about RSA, and then I'll move on.
No questions as of now.
Okay. So this brings me to the last part of my lecture, which is very brief, very, I'm not going to go into very much detail, but I want you to I wanted you to know that there is also work on thresholdizing quantum resistant schemes, since we know that Dice-Log and RSA are not resistant against quantum computing. So the first is a work that appeared a couple of years ago at Crypto, which shows that if we can build a threshold fully homomorphic encryption, then we can build what we call a universal thresholdizer. I thought when Dan came out with this word was, genius. It's basically a compiler that takes any cryptographic schemes and builds a threshold version of it, which what's really interesting is non-interactive. It thresholdizes the cryptographic scheme in a single round. And this work is very highly related to MPC computation in one round when you have a distributed fully homomorphic encryption. And in fact, in my mind, this is not just about thresholdizing cryptographic schemes, but it's about doing general MPC when you have threshold fully homomorphic encryption. So let's start with a candidate fully homomorphic encryption, for example, the Gentry-Sahai-Waters scheme, which is based on learning with errors. So in this scheme, the secret key is a vector of size L of integers modulo Q. And a ciphertext is a matrix of size L times M into the same space ZQ. To decrypt, take a column. So the matrix represents M bits. You take a column of the matrix, and you do the inner product with the secret key. And if the result of this inner product is small, then the plain text is 0. And if otherwise, the plain text is 1. And small is a parameter of the scheme, which depends on the security of your LWE problem. So you can do an N out of N scheme pretty I wouldn't say simple, but it's not that complicated either. You take your vector and you split it into N out of N additive shares. And then what you're going to do, a party I will compute locally the inner product of its share with the ciphertext, okay? Now, to avoid revealing information about its secret share, the party will add a small amount of noise to this inner product, okay? This is some sort of smoothing. In some of the literature, I think this is called smoothing. So now we have this partial decryption right here. And then, so we add this noise because we want to hide your secret share. And then, because the noise is small, when you add all the shares, the noise doesn't grow too much. And so the decryption test will still work. You know, there's enough slack there in your parameters that this added noise is still going to give you the same decryption, okay? So D is not going to be that far from the sum of the DIs. And so you can, the correctness of your decryption will still work, okay? Any questions so far? So, and this was...
No questions.
No questions. This was known before we did this work. So what is the problem with doing this with threshold? That if we split SK with Shamir, then, and we do this thing in which each party, it's basically very similar to the problem that we were having with RSA. It's still the Lagrangians, because now when we interpolate with the Lagrangians, with RSA, we had the problems that the Lagrangians had fractions and we couldn't divide. Here, the problem is that the Lagrangians are going to multiply the noise too. And that's going to make the noise of this linear combination much bigger. And it's going to bring this value far from D. And so your decryption is not going to work anymore. So what you're reconstructing is basically useless. Okay, so is it clear what the issue is with doing Shamir, right? So, okay, so we propose two solutions. The first one is don't do Shamir. There's plenty of secret sharings out there in the literature that are different than Shamir's. And in particular, what we want is a linear secret sharing. Why do we want it linear? Because we want the ability to compute the inner product efficiently from the shares, right? So by linear, I mean that you can compute a linear function over the shares. But the reconstruction involves only binary coefficients. Now, if that's the case, then when we reconstruct, because these BIs are linear, the noise is still going to stay small. And because it's still going to get small, this linear combination is going to be close to the value that you would get in the centralized case, and so decryption still works, okay? The question is, how expressive are these linear secret sharing with binary coefficients? Turns out that they are quite expressive. And I mean, this is something that surprised me. And in particular, they include threshold access structures. So we can do N out of T, T out of N, and more with this 0-1 LSSS. The drawback is that if you, in a way, tie your hands and not use Shamir and use this kind of combinatorial constructions, the size of the shares for the players grow. In particular, for N players, each player has to hold something on the order of N to the fourth shares. But we can do it. The other option is an option that is very similar to this factorial trick that Shoop did for threshold RSA, is that we are going to use Shamir. And then the first thing that we're going to do, we're going to remove the denominators, and with the usual trick of multiplying by n factorial, and then we just choose our parameters so that we can accommodate this noise growth. What is the disadvantage there? Now that our parameters are going to get, if LW parameters are already big to begin with, they're going to get even bigger. And even more troublesome is that now the issues of the centralized key are dependent on N. So it's almost like this encryption scheme that I put out there for people to use, people will know that it's a scheme that pertains to N parties. You know, it's not just the internal computation that depends on N, it's also the encryption operation is going to depend on N, which is something that we don't want. And bear with that thought for a minute, because we're going to be able to address it. But either way, we have it. We have a threshold FHE, neither of them incredibly efficient, but one of them with using this binary linear secret sharing, or with growing the noise parameters using Shamir. Once we have this threshold FHE, we can build a universal thresholdizer, which is a pretty standard notion in that basically we want to use this threshold FHE to do non-interactive MPC. So here's the idea. So you have a secret K, and your setup outputs a shares of K and a verification key. So you want to think of this is the secret key of your centralized cryptographic schemes. So a dealer is going to share them and is going to put out some commitments to all of this. And we're going to use this to verify that the players are behaving correctly. Now, once you've done this, what you're going to do, you have a circuit. This is your cryptographic algorithm. Think of it as a signature, which input X, which is your message, for example, and the share of your secret key. What you're going to locally do, this requires no communication. It outputs a partial evaluation of the circuit. Then there's a verification algorithm that verifies that this partial evaluation is correct. So you want to think of this partial evaluation that it includes some sort of proof of correctness. And then, given t+1 correct partial evaluations, you should be able to compute the entire value of the circuit, again, locally. So there is just one round of computation, which is one round of communication, which is every party broadcasts this value yi there. And how do you do this? It's basically a combination of threshold FHE with non-interactive zero-knowledge proofs. So the setup, you take what is the share of each party? The share of each party is the share of the threshold FHE. And if this is the secret key of your cryptographic scheme, you're going to encrypt it with the FHE, and you're going to commit to all this SAK. And this will give you the verification key. Now, on input a circuit C, X, VK, and share SAK, you can evaluate FA of the circular K of X using the homomorphism of A. So this eval does nothing. The first step of the eval just evaluates C on X and K using the homomorphism of A and G. And then your local evaluation is produced as the partial decryption of this encrypted computation, plus a zero knowledge of correctness, an indirected zero knowledge of correctness, that you're actually using the correct key, the correct SK, and so on. And then the verification checks the NISC, and the reconstruction uses the reconstruction procedure of the threshold FHE to decrypt the value. Right? So once you have this very powerful threshold FHE, there's nothing here really that says that C has to be a cryptographic function. It could be any function. So what are the application? I just say if K is the secret key of a cryptographic scheme, and C is, say, your signature, you obtain a one-round threshold version for any scheme. By the way, one interesting application is the compression of the non-succinct Shamir base threshold FHE that I showed earlier, because that scheme had parameters that grow with n, but you can feed this, you can use this non-succinct threshold FHE to build a non-succinct universal thresholdizer. But then you can use this non-succinct universal thresholdizer to thresholdize a centralized succinct FHE. So now what people see from the outside is not dependent on n anymore, right? And all the computation that depends on n gets back inside the network of players. This reminds me a lot of the boosting step of FHE, right? After a while, you sort of bring it back. You bring back the noise under control. And here, sort of, we're using this noise that grew up by doing the threshold. We bring it back through the same procedure. So I think this is, yeah, I think I'm done with that, with lattices. If there are any questions.
Yes, there's one question.
Yeah, go ahead.
A few slides back about growing the parameters. The question is, how big do the LWE parameters become? And does it become infeasible to compute FHE operations?
No, it doesn't. Your parameters grow in by n log n, right? Because you have to accommodate this n factorial. So they grow, but it doesn't become infeasible. It's just your Q and your L and your M have to grow by n log n bits. Okay. So large n, you maybe want to think about it, right?
Okay, no more questions.
Okay. Okay, so the last, I don't know, 10 minutes of this lecture, I wanted to talk to you about isogenies. That's because the last few months I've been trying to learn about isogenies. So I'm going to say, if there are people who are isogenies experts in the audience, I ask your forgiveness. I'm going to give a very, very simplified version of what isogenies are based on my very weak understanding of them. But I understood enough to know what are the problems when you want to thresholdize or distribute this computations. So let me give you a very brief one slide introduction about what isogenies are. So we have a set, a function called E. In most of these instantiations, E is a set of elliptic curves, which is endowed with a group action G. What do I mean by that? Simply is that if you take an element G in the group and a curve E in the set E, there's an operation that takes the group and the curve and gives you another curve in the set E, okay? So over this set, over this homogeneous space, we have our problems, which is given two curves, E and E prime, find the group element that maps E into E prime. This is the equivalent of the discrete log problem in the space. The other problem is given E and E prime, such that E prime is E acted upon by G, you want to find, and then I given another curve F, you want to find F prime, which is G acting on F. And this, you can see, is the equivalent of the computational Diffie-Hellman problem. Okay? So those are the hard problems in the space. The main difference with cyclic groups and discrete log is that basically there is no structure on the set E, which is the, so if I give you two curves, it's not like you can like multiply them together or something like that, right? So this is the source of the conjecture quantum hardness of these two problems. And in isogeny-based instantiation, as I was saying, E is the set of elliptic curves. And basically, the operation brings you from one curve to another. And you can take this curve, say, take this curve and this curve and multiply them. And there is no multiplication operation among the curves, right? Okay, so any questions so far? So this is the one slide about isogenies and
no questions.
Yeah. So, and here is how you build a signature scheme. Is a basically a riff on Schnorr's. You take a base curve. We're going to assume that our group G is ZQ with the addition operation. Okay. So Alice knows a group G such that F. So basically, Alice knows the quote unquote discrete log of F respect to E. And she wants to prove that she knows G. So she runs the following protocol. Remember, this is like Schnorr. So she's going to send F prime, which is E raised, the equivalent of raising E to a random value A. Then the verifier sends a bit B. And if B is 0, Alice answers with A. And the verifier checks that F prime was really computed as A times C. And if bit is 1, Alice answers with A G inverse, which really should be A minus G. And the verifier checks that if you take F and you apply C, then you get F prime, because the G cancels and you're left with A. This is exactly Schnorr with binary challenges adapted to the quote-unquote discrete log problem in isogenous. This proof can be turned into a signature scheme via the Fiat-Shamir heuristics, where the challenge is chosen as the hash of everything, including the message. You have to repeat it, obviously, several times, because this basic protocol has soundness and a half. So, okay, so how do you thresholdize this? So this is, on this side, I have the signature scheme. So let's assume that the dealer has shared the secret key. Let's not even think about DKG. We'll talk about that in a minute. But let's assume that the dealer has shared G via Shamir among the n parties with threshold T. So when T plus 1 parties want to sign, the first thing that they do, they can map their shares to additive ones. Remember, if you know your T plus 1 things, you can just scale them by their proper Lagrangian. And then each party selects a random value AI, and they perform this thing distributedly. But the first thing that they have to do is compute this F prime, right? Which is A times C. So if each guy has AI, the only way that we know how to compute A times C is to apply A repeatedly. So the first guy applies A1, then the second guy applies A2 to the result of the first guy, and so on. And the last guy will be F prime would be A times E, where A is the sum of the AI. Okay, so one thing that I didn't say in the previous slides is that if you apply two groups element in the in succession, then you're going to get the sum of the group elements. That's where there's this sort of homomorphism property of the equation. But you can only do this sequentially, because if I apply A1 and you apply A2, we end up in two different curves, and there's no operations in the curves that would allow us to combine A1 and A2 after we apply them in parallel, which we have with sklearn, right? So then you can, once you finish this n round computation, you compute the challenge B hashing, and then you just output. Here's a bunch of confusion because it's additive notation, this inverse is really minor. So I ended up not fixing the slides. And then you're done. And C is the sum of the CIs, right? So the main issue with this protocol is the sequential computation, because you cannot combine two separate isogeny computations done in parallel, because you're going to end up into different curves. What you can do is I do my first curve, and then you act on that curve, and then the next guy acts on the second curve, and so on. Okay? So this protocol right here is they described it just with a dealer and with honest but curious case. So then, okay, so how do we, and then we have a dealer, right? But the reality is that this protocol right here in the middle can also be thought as a DKG, right? Because they're basically generating a AI, a random value A, and the mapping of the curve under the combination of the A's. So this generation of these nonce can also be used as a DKG if you want. You have to sort of somehow make sure that this additive gets mapped into shares, but that's okay. It's sort of like, it's basically the equivalent of a Feldman VSS, with the main crucial difference that you have to do things in sequential rounds rather than in parallel, the way Feldman does it. As in Frost, we use the same Schnorr-like zero-knowledge proof to prove that we know what we're contributing, and this will give us malicious security with abort. Okay, so the ideas are pretty much the same. We're sort of leveraging this informal connection between sklearn and isogenies with the big caveat that everything that is in parallel with sklearn becomes sequentials with isogenies. Okay, and then finally, the last paper from last year sort of dealt with the issue of how do we get a robust DKG with guaranteed termination and fairness and uniform distribution so that we can do proof by simulation. And in this, we need to notice that the most important thing here is that in the setting of isogenies, there is no equivalent of a Pedersen VSS, right? Which is what we used to get this fair, robust DKG. Why? Because again, Pedersen is really based on the fact that I do a sharing of my secret and a sharing of a random value, and then I multiply them together. And there is no way to multiply these two things together in an isogeny setting, right? So there is no way to do this information theoretic Pedersen thing. So what they did was create this non-malleable VSS. I'm still wrapping my head around this paper, using zero-knowledge proofs. And this gives you the non-malleable and recoverable properties that, if you remember from yesterday, we talked about are needed to get this joint VSS computation work, so that we can always have the protocol terminate with the right target public key. However, the combination of the secret keys into a unique public key remains inherently sequential due to the lack of structure of the isogenies. And a student of mine and I have been sort of looking at this for a while, and then we realized, oh my God, this is exactly why it's quantum resistant. If we were able to do this, we would probably be able to adapt the Shor quantum algorithm to work for this too. So, and actually that would be an interesting question to ask. If you were able to do something like a Pedersen DSS on isogenies, would that mean that isogenies are not quantum resistant, right? So I'm done with the technical material, and I think I'm also done out of time, but allow me one slide, again, with my target audience in mind of graduate students who are getting into research. Here is a very non-exhaustive list of open problems. The first one is a truly scalable DKG that requires less than quadratic communication. Can we use recent advances in SNARKs and, or at least what I mean by less than quadratic, at least the public communication that everybody has to look at, because sometimes that's what goes into a blockchain. So you want to make that as small as possible. Can we use recent advances in SNARKs to do that? Can I just put a very small proof that everything is correct? So in theory, we can. The question is, can we actually build it, right? Lots of these problems have a theoretical component, but they also have a engineering optimization component that are really both fascinating in each side, right? Better proofs. One thing that I didn't mention was that the threshold DSA protocol that I showed you yesterday has a proof in the universal composability framework. I am not aware of a UC proof for Schnorr. The proof that Frost does have a proof for concurrent executions of Frost, but not a proof for UC. I don't think it would be too difficult to get it for Frost or to modify Frost in a way that wouldn't lose much of the efficiency beauty of Frost and get a full UC proof. So that, in my mind, that's kind of a low-hanging fruit. People who have familiarity with UC proofs may want to look at that. So we have this really beautiful result about, FHE-based universal thresholdizer, but is it theoretical? Is it practical? FHE has been making great strides, and at what point it pays off to say, forget trying to build threshold DSA from scratch. I'm just going to, or the next threshold scheme, I'm just going to call my universal thresholdizer, maybe tailor it in some way and get my threshold, my one-round threshold version. And by the way, a similar question can be made for MPC, right? MPC has been making greater strides than FHE. At some point, and I'm sort of killing my own research area in a way, at some point it may be worth, and this is actually a question that everybody should ask when they design a threshold scheme, what am I gaining with respect to a general MPC solution? And finally, can we have threshold isogeny-based schemes that don't have this sequential rounds structure? And as I said, I believe that it might be inherent, in which case can we prove that if there is a constant round threshold isogeny scheme, then it has to be necessarily not quantum resistant, right? Then you're basically going back to Daskel log or something like that. So those are the questions that I'm thinking of. So those are the questions that they're not the only open question in the area, and there's plenty more. And I think this is the end for me.
Thank you, Osayo. Thank you for this wonderful series of lectures on a very timely topic of threshold signatures, which enjoys a lot of interest now, and there's still a lot to do, as you said in your last slide. I would also like to thank everyone who participated in this winter school. I would like to thank the lecturers, Gilad Asharov, Elet Boyle, Henry Corrigan-Gibbs, Sarah Gennaro, Yuval Ishai, Dima Kogan, and Peter Scholl. I would like to thank my co-organizers, Karmit Chazai and Movite. I would like to thank Yonit Homburger, our administrative manager, who worked behind the curtains and made this thing possible. And I'd also like to thank the students, representatives or moderators in this session. There were Christian and Raul, who forwarded questions from the other students and enabled the school to be interactive. I also want to thank our sponsors, which were Protocol Labs, a lot of companies which might be relevant or interesting for students or graduating students. Protocol Labs, where Rosario is working, Technology Innovation Institute, TII, Algorand Foundation, LatticeX, Starkware, Input-Output, and Duality Technologies. The theme of the school this year was on advances in secure computation. We wanted to show things which were of a lot of interest in recent years, both because there are interesting applications or because the recent improvements and results that we thought that people should know about. Interestingly, a lot of these results, most of the results were in the two-party setting, where there are only two parties. And that's interesting because you would imagine that when there are more parties and you have an honest majority, you will achieve better performance. But still, it seems that there were a lot of interesting results in the two-party case, and it's actually used in many settings. So something I would like to ask you to do is to think about topics for the school of next year. And if someone is interested to learn about something and think that others will also be interested to learn about it, then drop us a line, and we're happy to get ideas and run an even better school next year. So next year we hope to see you all in person in Tel Aviv, Ramat Gan, Israel, where we are. We hope that the weather will be nice. And those who didn't get to come here, well, at least you can, you should know that the weather here was not nice during this week. There's 50% chance of it being good or bad. So this week was maybe the worst weather we had in any of the winter schools. So it's not so bad that we couldn't do it as a physical school. And yeah, we'll be very happy to see you next year. And with this, we'll conclude the school. Thank you, everyone, and bye-bye.